Okay, good morning, everybody. It's a great pleasure for me to introduce this morning's speaker, Emmanuel Candes, even though he needs no introduction. He's a French statistician, world-renowned for his contributions to the field of compressed sensing and statistical hypothesis testing. He's a professor of statistics and electrical engineering at Stanford, where he holds the Barnum-Simons Chair in Mathematics and Statistics. He has a whole string of awards and honors to his name. I will just go quickly to some. He's got the NSF's highest prize, the Alan T. Waterman Award, the 2017 MacArthur Fellow, the ICIAM Collatz Prize in 2011, the George Polya Prize from SIAM with Terence Tao, the Lagrange Prize from the Continuous Optimization from the Mathematical Optimization Society, and I should mention the Danny Heinemann Prize in 2013 from the Academy of Sciences of Göttingen, and the David Perkhoff Prize from the AMSIM, and he's been elected to the National Academy of Sciences. This is just to give you the list of the diverse organizations which had the prescience to award his work. Today he will be talking about something quite different from some things that he's done before, sort of new area of the frontiers of conformal and model-free inference. None of you want to listen to me, so I will quickly hand over the stage. But I just want to say quickly that the Bernoulli Society is delighted to present to him the Bernoulli Lecture this morning. So.
Thank you very much. Can you hear me? Yeah, okay, good. So thanks, Kavita, for the very kind introduction. And I know it's early, so thanks for being here. It's a real pleasure and honor to be addressing such a distinguished audience. And today I'll talk to you a little bit about what is beyond conformal prediction. So to start with, I don't think I need to convince an audience such as this one that we use machine learning predictions and AI systems to trigger very important decisions that impact our lives in very critical applications. For example, we use AI systems to decide which treatment you're going to receive, to decide whether an inmate is going to be paroled or not, who is going to win the next election. And the question is, as we are using these fancy AI systems, the question is, can we have confidence in these predictions when the decisions they trigger are so critical? And so one way to assess the uncertainty of AI systems, and I think we all know that essentially deep learning architectures are a bit too confident about their prediction, is to think about prediction set, which is a construct that has been very useful in recent years. And the definition of a prediction set is completely straightforward. I give you some data, training data x1, y1 through xn, yn, and I give you a test point xn plus 1 for which you do not see the label. We're going to assume that this data is exchangeable. If you don't know what that means, you can just imagine that the IID. And a prediction interval is an interval constructed from the data I gave you that has the following property, that it must contain, for the test point xn plus 1, it must contain the true label, let's say 90% of the time. So that's the definition of a prediction interval. And so we want this to hold in broad circumstances. That is, we want this to hold no matter the distribution underlying the data mechanism, the distribution mechanism, any p of xy, which I know nothing about, no matter the sample size, I'm not interested in asymptotopia here, no matter how complicated your prediction rule is, I want to be able to handle GPT-4, as we'll see later. So we want this, and it's not clear a priori how we can do it, but we can do it thanks in particular to the wonderful line of work started by Vladimir Vogt that goes under the name of conformal prediction. So I'm going to quickly review conformal prediction. It comes in several flavors. We have full conformal, we have split conformal, we have more efficient variants of these strategies. But because we have probabilists in the audience, I'm going to tell you a little bit about full conformal because this is perhaps the cutest of them all. So it's quite easy to understand. So you give me a data set, and because I can only plot in the screen my data distribution, I have 2 dimensions, an X and a Y. And you give me this data, and the boss comes to me and says, Emmanuel, I would like to create a prediction interval at xn plus 1 equals 4.7. And I say, all right, here's what I'm going to do. I'm going to hypothesize a value of little y. This is a red dot you see here, right? So there's a little red dot. I say, could little y be a reasonable value for yn plus 1? And then I'm going to fit a model, including this data point with a red dot. And so I get a model. I'm going to calculate residuals. Here they are. These are the model errors. And then I'm going to see, the test residual, this residual that we see in red, how large is it? How unusually large is it? And so here we can see that it's in the top 27% of all magnitudes. Okay, so it's not an unusual residual. And so now I'm going to move the red dot, I'm going to increase it, and I'm going to repeat this stuff, fit the model, compute residuals. How unusual are you? And here we see that it's a bit larger, so in the top 22%. And then I keep on doing this. And you see, now the residual is getting larger and larger. Now it's at the top 17%, 15, and so on. So you do this. I'm very proud of this animation because you can see that the red dot is actually pulling the black curve, if you look carefully. So it's pulling the black curve, as it should. And now the residual is the largest. And no matter how you go further, it's the largest, it's the largest residual. And so the prediction interval I'm going to construct is very simple. I'm going to look at all values of little y for which the residual is not unusually large. That is, it's in the bottom 90%. Okay, so this is what I'm doing. That's a prediction interval I'm going to return to my boss. You'd say, well, it's expensive. You have to refit the model many times. I agree, and that's why we have alternatives to this, which I will not discuss today. And this actually works. So why does this work? So this is putting in math what we've just seen in pictures. This is the data you gave me at the top. I'm going to impute a little y, and I'm going to fit a model on all the data point n, xn plus 1, and y, and I'm going to compute residuals. And I'm going to check if the residual with this little y is in the bottom 90th percentile of everything I computed, or the residual I computed. And the key argument that I hope my probability friend will appreciate is that if little y happened to be yn plus 1, then there is no way you can distinguish the test residual from the training residuals. If my algorithm is symmetric in that it treats all the points, the order in which I give you the data point doesn't matter, which is pretty much always the case, then if I plug little y equals yn plus 1 in here, then the residuals are exchangeable. So I cannot tell you, by looking at all residuals, I cannot tell you which one is a test residual, which means that the test residual has a 90% chance of being in the bottom 90%, and therefore, yn plus 1 is included with probably 90%. And exactly what conformal prediction affords you is by running this simple algorithm and using the fact that we have scores that are exchangeable, then I can guarantee exact correctness. So this works great, and so people are building prediction intervals left and right. And so this is an example of a data set on the left that follows a recipe we've just seen. And one weakness of the recipe we've seen is that basically I'm going to fit a regression function and create a prediction band around the prediction function with sort of the quantile of the errors. And that's maybe, in case of heteroscedastic data, a poor idea. And so we have many other ways of constructing prediction intervals, and they depend on which score you're going to use. And so on the right, you see a method we introduced in 2019 called conformal quantile regression that's going to take a completely different approach to construct prediction intervals by essentially fitting conditional quantiles. They won't be calibrated, but then I'm going to just run the conformal machine to calibrate them. And so in general, how conformal prediction works is you pick any conformity score you like, any statistic you like, and that's why we can construct lots of different prediction intervals. They will all have marginal guarantees. You pick any conformity score you like, S of xy. The example we've seen on the slide is a case where I'm just looking at the magnitude of the residuals, so y minus mu hat x in magnitude. I get my conformity scores on the training data and the test point. And I'm going to include you if you're in the bottom 90%. And no matter what score I'm taking, as long as I'm using a symmetric algorithm that treats the point symmetrically, I'm going to contain the true label 90% of the time. And so when you use careful conformity scores, then you get prediction bands or prediction intervals that look really, really good. OK, so this is conformal prediction in a nutshell. It's been applied left and right. This is another paper of ours where you can extend this to discrete labels. And so you have a bunch of images, and you have to label them. And you see underneath these images the conformity sets that we produce. And the first one says, I'm pretty sure that it's a fox squirrel. And the second one, I'm less sure about what I'm seeing here. And what I like about conformal prediction, it says, when the size of the prediction set increases, it means that the algorithm is less sure about what you're seeing. And so I think that's a really, really good way of measuring uncertainty. As I said at the beginning of this lecture, I'm not really here to discuss conformal prediction. People are building prediction sets, and they're using them. But it has been my experience that people don't really need prediction sets. They need to do more. And so what we're going to see is how we can leverage the ideas of conformal prediction to do way more than constructing prediction sets so that we can address real practitioners' needs. So I'm going to look at two little stories, to show you that there's a lot of life beyond conformal prediction. And the first one is going to be about drug discovery and how can we select drugs for further experimental testing in a way that is reliable. And second, which is the question of the day, is we want to say something intelligent about the factual correctness of large language models. So I propose we go through these two stories. So the first one, which is really about model-free selective inference, but really applied to drug discovery, is work with Ying Jin, who is a wonderful PhD student at Stanford and who will join UPenn, the Wharton School, soon. So, there's a lot of buzz at the moment that drug discovery is changing. It's changing because of AI. What do we mean by this? Is before, to kind of design new drugs, we are doing in vivo experiments. And now we move to in vitro experiment at some point. And now we move to what I'm going to call in silico experiments, where we're going to use the predictions of AI system to understand which drugs we should pursue. So there's a lot of excitement. As you can see, the future of biotech is AI-driven drug discovery. And so, what do people try to do in drug discovery? You have a library of compounds, which is enormous. You have a target molecule that's your target disease, and you would like to say, for example, find in this huge library of compounds, molecules that have a high affinity for your target. And to do this, you can make experiments, of course, but they are very costly and very expensive. But now we have things like AlphaFold and other things, so you might use AI to predict the affinity of a compound for a target disease. And that's what people are trying to do. They're trying to do this, instead of going in the lab, they're trying to do this with AI instead. Okay, and it works so-so. So AI gives a lot of false leads. So by following the prescription of prediction algorithms, you can spend your time doing uninteresting stuff. And so we have to be careful with what we do. So I would like to explain here how statistical thinking can help alleviate this project. And I should say that we worked on this, and then Genentech got interested in what we're doing, and we're starting a collaboration with Genentech on stuff of this kind. So can we calibrate these black box models to make better decisions so that I send to the lab drugs that are actually worth investigating? I'm not going to waste my time. So the way we can think about this in terms of machine learning is I have a prediction model, mu hat, that predicts from very complicated data, the sequence of amino acids, the chemical features of a drug, whether its affinity for a target. And then the response is binding affinity. It can be binary. Is this drug active or not active? Will it bind or not? Or it can be more continuous. It's a measure of how active it is. And so I have a data set, Xi, Yi, which are the drugs that have screened, the drugs for which I have a response, Yi. And there are very few typically. And I have a lot of test samples, Xn plus J, Yn plus J, and I don't know their Ys. And what I think a lot of people want to do in the field is to find those drugs that would exceed a certain threshold. I would like to be able to identify drugs that pass a certain benchmark that can be random or not without too many errors. Because if I have a lot of errors in the drug I'm selecting, I'm going to send them to the lab and I'm going to waste a huge amount of time. So that's a goal. So people have looked at conformal prediction to do something like this. And so now that we know how to construct prediction intervals, then maybe we should look at our prediction intervals. And, here are my candidate drugs. And I see two drugs, drug n plus 3 and n plus m. They seem to have sort of tight prediction intervals that are quite high. Maybe I'm confident that these drugs are active, and maybe I should test them. Should I select these two drugs and send them to the lab and spend a lot of money studying them? Should I run a clinical trial on this stuff? So, well, we have to be very careful with that, because the promise of conformal prediction is that you're going to get perfect marginal coverage. So if I look at all if I set an error rate, and I'm looking at the fraction of time that my prediction interval will miscover, I get the straight line. I get this black line. This is the theorem we've seen before, is marginally I'm doing the right stuff. But after selection, I'm not doing the right stuff. And so the problem is that we have a huge selection bias, which is that if now I decide to select those drugs for which the prediction says you're active, and I'm 90% sure that you're active and not inactive, the error rate is not 10%. The error rate is much higher, as you can see from this picture. So this is actually real data. And so we can say that if I were to select all drugs for which the prediction set is you're active, the error rate would be at least above 90%. So I would spend an enormous amount of time pursuing useless stuff. So even if I wanted 99% nominal, I'm going to get a 30% error rate. And so this is a problem of selection. So we're going to have to address this. So we cannot just apply conformal prediction out of the box. We're going to have to do something clever about it. Okay, so because we're statisticians, we can think about doing something a bit strange, which we want to essentially make discovery while controlling the false discovery rate. So what is the false discovery rate in my case? I would like to find those drugs, so I would like to find a set R of candidate drugs, while the expected fraction of false discovery, so what is the false discovery? It's a drug I'm sending to the lab whose actually outcome is below threshold. And I would like this fraction to be small, let's say below 20%. And if I can do this, if I had a method that would do this, then by controlling the false discovery rate, I would guarantee that, well, most AI-powered decisions are correct, and that when I do resource allocation, it's efficient. I'm not wasting my time. I'm not wasting my graduate students' time. I'm not wasting the government's money. I have a form of efficiency. So can we do this? So we're looking at something a bit strange because we're not looking at statistical hypothesis in a common sense. There's a random outcome, yn plus j, and I'm asking, is it going to be, the null hypothesis is going to be below cn plus j, which can also be random. And so we're going to think about this as, is it possible to construct a model-free, calibrated confidence measure, like think about it as a p-value, so to speak, and then can I look at this p-value to determine who should be sent for testing and who should not be sent for testing? And so this is a bit challenging because, I don't have hypothesis in a traditional sense. I have no modeling assumption. Nothing is following a model that I know. I don't know any distribution. As you'll see, the p-values are dependent, so we're in new territory here. So what are we going to do? We're going to try to learn and leverage a bit what we've learned from conformal prediction, but we're going to have to extend it in a significant way. So we're going to construct a conformity scores, a function S that takes a covariate, a feature, variable x, and a label y. And I'm going to ask that this conformity score be monotone in y, so that if you increase y, the score increases. So lots of example. Y minus your prediction would be a good example. Y minus your prediction standardized is also increasing in y. It could be your estimate of the CDF at y given x. So a lot of things are monotone in y. So we're going to take one of these scores. And again, choosing the right score is what is going to give us power. I'm going to look at the library of compounds I have, for which I have a y, and I'm going to calculate my scores. I cannot calculate test scores because I don't have their y's. So I'm going to calculate the test scores at the threshold. So I'm going to calculate S hat n plus j, which is the value of the test score at the threshold Cn plus j. So I don't have yn plus j, so I'm going to put the threshold, your cutoff. And then with that, I'm going to look at, if I were to plug the cutoff instead of y, how small is the test scores with this compared to the calibration test scores SIs? So I'm going to calculate, and you'll see that I have the right to think about this as a p-value. We're going to see this in a second. I'm going to calculate a measure of confidence, pj, which is looking at the rank of S of the test drug compared to the calibration drugs, the training drugs. All right? And so what we're going to say is if the p-value is very low, it means that S hat is very small compared to the SIs I've seen, it is very likely that this drug is of interest to me. Now, we can reinterpret these p-values as follows. I've shown you how to construct prediction intervals. We can think about this pj as the smallest alpha at which the prediction interval for my drug is entirely to the right of Cn plus j. Okay? So there is evidence that this thing is doing well. But the real result is that, yes, it's actually a real p-value in the following sense. That is, the chance that pj is less than alpha, and whenever my null is true, that is yn plus j is less than Cn plus j, then that's at most alpha. So it's a very well-calibrated measure of confidence. So very small p-values probably means that my drug is of interest to me. And now we need to select. Now, these p-values, as you can see, they're all dependent. Why? Because they're all referring to the calibration set. So they have a lot of correlations. But the correlation they have together is kind of positive. They have a form of positive correlation, which is going to be tremendously helpful. And so this is where the work becomes very technical, and I will skip all technicalities. But we are going to need to do multiple testing with dependent p-values, but the p-values we've just introduced are a form of positive dependence, and it's usually good for testing. And so after a lot of work, you can show that the simple method, which is this, which is you calculate the p-values with the formula I just gave you, and then you apply Benjamini-Hochberg, then surprisingly that works. That works in the following sense. That is that you control the false discovery rate exactly at level Q. And so what's kind of nice about this is there are no modeling assumptions. You can use prediction engines that are as complicated as you wish, and I'll give you examples of what we do, and you have FDR control. And in real life, so we've tested this on real tasks, plenty of different data sets, plenty of crazy prediction rules. We have convolution, we have graph convolutional neural network, we have stuff I don't even want to know about it. They're so complicated. And we test them on plenty of different data sets. And then we have on the x-axis the FDR target. On the y-axis, we have the realized FDR. And you can see that we're hugging the 45-degree line. We're always below, not much below, and we're hugging. So you have, it's a theorem, but it's also something you see in practice, which is really good on real data sets, with real drug, real AI systems, and all of that. Now, one thing I should mention is that in a lot of applications when you do drug discoveries, and so what these methods do is they would actually allow you to examine library of compounds that have at least hundreds of thousands of compounds. The one that are of interest to you are usually in the hundreds, and so you're going to be able to go down to a few hundred discoveries while maintaining FDR control. Now, one thing that you have to pay attention to is that in a lot of applications we work in, I mentioned that we work with two groups. First, the group of Yuri Leskovich at Stanford, who is a computer scientist and friend of mine, and then Genentech. We have, in a lot of cases, we have a mismatch between the test data and the calibration data. And why? It's because you are entering the calibration test if I measured you, and if I measured you, it's because you looked interesting. So you're not exactly representative of the compounds that I wish to examine. And so typically, you're going to have a covariate shift. That is, you have that when you look at the likelihood ratio between the test data and the calibration data, it does depend on Y, because the activity is a physical thing. Given X, it doesn't change. But what does change is the distribution of X. And so you're going to have to deal with this. And what I just want to say that there's a way to deal with this, and we have a second paper with Ying that deals with covariate shifts, where you're going to modify your construction, you're going to modify your selection rule, because BH does not really work anymore, so you're going to have to do something a bit different. But at the end of the day, you're going to have exactly the same guarantees. You're going to have tight FDR control. And so this is something we're seeing with Genentech. So these are real experiments about a lot of different things, where in the first experiment, we're looking at gene perturbation. We're interested in finding perturbation that would lead to high proliferation of T cells. In the second experiment, we are interested in finding proteins that are stable across different environments. They will not just degrade as you change the environment. In the third experiment, we are interested in drugs with low inhibition rate, that is, drugs that have a certain functionality and are not toxic. In the fourth experiment, we're doing something even crazier. We're trying to predict the outcomes of clinical trials. And in all these experiments, we've tried our methods, and so these plots are a little bit boring, but what you can see, the red line is the y-axis is a realized FDR, the x-axis is the target FDR, and you see we're always hugging this 45-degree line, while naive methods would have serious violations of FDR. Conformal methods that do not take selection into account. And so across a wide variety of experiments, we managed to maintain FDR control, and so that's that. And so as I said, you have a picture of Yuri Leskovich at the top, and then the logo of Genentech. Okay, so this works well in practice, so we're happy about that. What's very fun about working with companies and people in the trenches is that they say, well, but Emmanuel, what you're doing is great, but we'd like to do more, and so we're working on more. I'll just give you a sense of what is more. You do not want, so if you think about chemical space as a huge space, you don't want all your discoveries to be in the same location. You want to explore chemical space. Think about using this stuff to hire candidates. You want diversity. So the thing is that we're working on now is how can we make discoveries that are not basically all the same molecules, or things that are too close to things you already know. So a big challenge is to extend this work, which we're doing at the moment with other PhD students from Stanford, to situations where, well, we would like to control FDR because we don't want to waste money, but at the same time, we would like to explore chemical space. And so that's what we're working on. All right, and so in this last part of the talk, I will talk about the question of the day, in my view, and maybe this is an invitation for statisticians to join this field. I've been completely blown away by language models, but also like you, I've typed, who is Immanuel Candace, and ChatGPT told me a lot of BS about Immanuel Candace. And so we're going to talk about how we can assess the correctness of the output of language models, and this is work with two extraordinary students at Stanford, John Cherian and Isaac Gibbs. And really here, I'm really, just like for the drug discovery, I'm the messenger here. Like they are really the people doing all the work, and I'm just basically relaying what they've done. Okay, so before this conference, I had a bit of fun. I said, please write a detailed and concise one-paragraph biography of Nicolas II Bernoulli, because this is a Bernoulli lecture. It's one of the Bernoulli members of the not the most famous ones, and I did this on purpose, as you'll see. And ChatGPT was very happy to oblige and wrote a biography of Nicolas II Bernoulli, and this is what it says. He was born in 1695, died in 726, was a Swiss mathematician and member of the renowned Bernoulli family, and blah, 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 and makes a series of claims about the life of Nicolas Bernoulli. Some of them who are good, you'll see that some of them are correct, but some of them are not correct. So Peter is a Swiss mathematician and probably is able to tell us already what is wrong and what is correct. You can do it in a rap form. So Peter has many talents, so he can tell us, he can probably parse this bio and tell us what is correct and what is incorrect. There are correct statements and quite a few incorrect statements. So what we built is we built a system. This is not heroic. We built a system that would take an output like this and parse it into a series of claims. And here are a bunch of claims that we can parse. So we built a system to do this, but we use the language model itself to do this. And so a claim is Nicolas Bernoulli was born in 1695. Another is that he died in 726. He continues to influence people to this day, and so on. Now, some of the claims are correct, some are incorrect. There are thousands of papers on hallucination detection and claim storing. Like, it's an exploding field. I'd like to see members of this community engage with this topic because it's extremely important. And so what I did is, when I say I should say what John and Isaac did, is that we asked ChatGPT to rewrite 5 times. And I got different answers each time. Nicolas Bernoulli was born in 1695, died in 1726, was a Swiss mathematician. But look at the last time, he was born in 1699 and died in 1724. So it's a different claim. So now, the thing about language models is that you can use language model to score the factual accuracy of a claim. For example, one way to build a score is to say, to play the games I've actually did here. You ask ChatGPT the same thing many times, and you say, how many times did you tell me he was born in 1695? And if this is a lot of time, then you're going to get a high score. If it's not many times, you're going to get a low score. Or you can even ask LLMs to tell you about how confident they are about what they're telling you. And that's another way of scoring the output of an LLM. But you use the language model itself to score itself in a clever way by prompting it, by doing experiments. And so you can create scores. And so the first step to actually remove false claims was actually proposed by 2 colleagues of mine at Stanford, Mori and Hashimoto, very recently, this year actually. And what you do is, well, we have Euler was born in Basel, Switzerland, so it has a high score of 3.7. It's actually true. And so you create a data set like this, where you have a bunch of claims, you have a score that the language models or you carefully manipulating the language model will give you, and then you have whether it's correct or not, that you need a human for that. And then we're going to apply a straight conformal approach. Then I'm going to compute a threshold for each person I'm going to compute a threshold at which all false claims are filtered. So I take a biography of Peter Buhlmann, and maybe the threshold will be 4.1. And what that means is all claims that have a score about 4.1 about Peter are correct. But at 4.1, there is an incorrect one. Okay? And so I have these scores and have my annotation. And that is a conformity score. And now we're going to just unroll the conformity program, and that's what Mori and Hashimoto did in very different ways, because they don't really have this language. And I'm going to compute for, so I get these scores. For Euler, the score is low, it's 1.6, and because Euler is famous. And so the conformity score for Euler is low because most of the claims about Euler are actually correct because he's famous. Brad Efron is also famous, but not as famous, and so its score is a bit higher. And so then I'm going to calculate the 90th percentile of this score, which happened to be 4.1. And then here is the guarantee from conformal prediction. If I filter all claims about 4.1, what you see is 90% correct. So haven't we solved the problem? With 90% chance, this essay is entirely correct. With 90% chance, this thing you ask an AI system to automate is correct. Great. The problem is, what is left? Here, nothing. You can't even believe that Bernoulli is Swiss. So why is that? Well, maybe my scoring function is weak. Maybe 90% is too optimistic. Maybe the marginal threshold estimation is not the right concept here. Like, I cannot go to OpenAI with a system like this and expect that I'm going to be well received. So we're going to change that, and I'm going to tell you in words what we're doing to address this problem. But we develop a system which is based on statistical ideas, based on refining these conformal prediction ideas, and it does the following. So it does three things, and I want to be clear about what it does. One is, I'm going to force the system to retain approximately 70% or more of the claims you're making, because I don't want to print void statement or just say, Peter is a male. That's not useful. So you're going to have to retain 70% of the claim. But now I'm not going to be able to say that I'm correct 90% of the time. So I'm going to have to say, what is a chance that is correct, that you're correct? So I'm going to say, well, maybe the chance that you're correct is 63% now. And what does this mean? Where is omega? There's no omega in this world. So what I mean by 63% is well calibrated. Each time I say 63%, and I were to look at how many times the statement is, what is printed is correct, it will be exactly 63%. So I mean this in a frequency sense like this, in the sense of calibration. And the second is, and that's very important in language models, is I would like my validity to be correct no matter the person I'm discussing, kind of. So maybe no matter the person I'm discussing is too much to ask, but no matter the topic, no matter whether it's a toxic topic or not, no matter whether a person is famous, not famous, I have the guarantees that no matter the group the prompt belongs to, the correctness still holds. So I want a form of conditional assurance. So when we actually do apply our system to Bernoulli, we get this. So we say, this is what's left. So it strikes out a lot of claims. It keeps quite a bit. By the way, what's in bold is actually what's wrong. And so it removes one true claim, that it was famous for the study of differential equation and probability theory. And what the system will tell you is that this has a chance of 35.1% to be true. And what I mean here is that if you make thousands and thousands of experiments and you look at all the times the manual says 35%, you'll see that 35%, it's actually true. Not 37, not 28, 35. So now, We apply this to a lot of different data sets. This is a medical Q&A. So you ask ChatGPT, you have some symptoms, you ask medical questions, very sensitive areas. And here it's very important to have a form of conditional validity because you don't want ChatGPT to always be wrong on some kinds of medical claims and always be correct on other medical claims. And so here is basically the calibration I was talking to you. This is my advertised levels, the nominal levels. This is what I report. And then on the y-axis, you see what's actually being realized. And so you see a straight line, which is exactly the calibration we talked about. And then the box plot at the top, the green box plots, what they are is that the number of claims I can retain from ChatGPT when asked a medical question. And this retention rate is much higher than if I were to play a straight game. And I would say, please, ChatGPT, give me statements that are 90% correct 90% of the time. And in which case, I would have to get the box plots on the left, the blue and orange box plot, which are much lower. I would have to eliminate a lot of claims. Now, what's the difference between blue and orange is because we're going to try to boost the conformity scores. So we're going to apply machine learning to discover good scores that allow us to retain as many claims as possible. And so there's a technical innovation here that has to do with boosting as well. OK, so this is what we're doing. And now I'm not telling you how we get these results. So the way we can formalize this a little bit is to say, well, we have, again, as before, we have prompt claim annotation tuples. So P is your prompt. C are the set of claims made by ChatGPT. And A is basically whether these claims are correct or not. Then there is a conformity score, which we defined earlier, which is that I have a scoring function that I can score my claims. And I'm going to look at the max of this score, such above this score, every claim is true. That's my conformity score. And what we're going to try to do now is going to say, well, we could compute a quantile of these scores, but then that's not helpful. We need to be adaptive. And so we're going to try that, for each prompt and each claim, we're going to try to find a level at which we should report claims that is adaptive to get the kind of guarantees I just gave you. So we're going to try to estimate for each claim or for each query a tau I, which is a level adaptive level at which I should report stuff. And how are we going to do this? Well, this slide is really packed, so I apologize. It doesn't have much on it, but it says a lot, I think. We are going to try. So I have my Pn+1 is my test prompt. And I'm going to estimate levels at which I should make statements. And these are the alpha PIs that we see here. And I'm just going to basically run a form of quantile regression on the conformity scores to understand at which level I should make a statement. So formally, the way this works is we have a bunch of pinball loss, which is a loss that you see in quantile regression, with different values of the confidence, with different values of alpha, depending on the type of prompt you are. And then we are solving an optimization problem, and then we are keeping the claims such that when I plug S in this optimization problem, I get an optimal function G of S, such that tau hat is the largest value of S, so that S is less than the function that I'm fitting evaluated at S. So I know it looks a bit complicated, and you would not even know how to compute this. And so it looks a bit abstract at the end. For those of you who are familiar with conformal prediction, I would say that if all the alphas were the same, this is full conformal. This is just full conformal. If all the alpha PIs are equal to alpha, you're just running conformal, which is not obvious, but that's what you're doing. But now we're running conformal on data-dependent thresholds. So you run this. With this, you get a confidence level at which you're going to say something about the prompt Pn plus 1, the test prompt Pn plus 1. And what the statistical statement is that if the function class you're fitting is a linear combination of group indicators, so whether the person I want a biography about is male or female, whether this person is dead or alive, what countries they live in, this can be overlapping groups, then the formal statement you have is that what's going to come out of this, your scoring function at this particular threshold is going to be factual, conditioned on group membership, on the type of prompt I pass to GPT, toxic, not toxic, about a famous person, not famous, and so on, is exactly 1 minus alpha. So this is an informal description of our main result, which is that you get exactly what you want. When I say 1 minus alpha, I mean 1 minus alpha. So this is an informal view of what we promise. Okay, so there is perhaps a difficulty in computing this tau. So we need to compute tau, and so this is a bit tricky how I'm going to compute tau. Thank you, Kavita. So I'm going to compute tau, and so tau is whatever comes out of this thing that is quite abstract. But this is where the genius of John and Isaac comes in. They realized that we could compute this tau threshold quite efficiently. And let's say that this is my optimization program. And because I'm dealing with pinball loss, everything is linear LP representable, so it's a linear program. And so every linear program, and so basically solving the linear program is you have a linear program that you see in primal form on the left, and this program has a dual form. And by looking at the dual, we can say a lot of stuff. So we're going to ignore the primal problem. We're going to look at the dual problem from now on. So let's look at the dual problem. And the dual problem is that the dual variable is a proxy for coverage. And so, checking that S is less than what I want, the condition is the same as the dual variable is less than 1 minus alpha n plus 1, the alpha that I want to use. And the good thing is that the dual variable, as you vary this value of S, the dual variable is monotone in S. And so we're going to exploit that fact to calculate the right threshold for your prompt. And the way this works, maybe I have a picture. This is the proposed value of S, and this is the upper quantile that I'm fitting, the function g of S. And I can see that S is lower than g of S, and the dual variable is minus 0.04. So S is not large enough. So let's increase S. So we increase it, we increase it, we increase it. The dual variable is still minus 0.05. We increase it, we increase it, we increase it, we increase it. I'm touching g of S, but the dual is 0.2, is not 0.95 yet. So I'm increasing. So we have a movie. And then this is the last point. The dual variable now saturates at 0.95. This is the value of S I'm looking for, and therefore I have my threshold. And so because we're solving simple linear programs that have a lot of structure, we can basically calculate a threshold in milliseconds. And so on all the test examples that we've looked at, we could actually compute these thresholds in something like 50 milliseconds. So we have so there's some innovation about that, but we have fancy algorithms that will do this for you. Okay, so I'm running out of time. The last thing I've not said is like how you're going to calculate this alpha pi that goes in your optimization. So what you're going to do is you're going to run a full conformal method at fixed levels, 0.01, 0.02, and so on. For each prompt, you're going to find its alpha i's, which are the smallest alpha at which you can retain the 70% of the claims we were talking about, the claims that preserve at all levels. And then I'm going to featureize a prompt. That's what the language models are so good at. I'm going to featureize a prompt, and I'm going to fit a function that tries to interpolate this alpha I from the features phi of pi. That's sort of schematically represent this. For example, a feature might be, how many views does the Wikipedia page have? If I want to write a biography about Peter, and Peter has a wiki page, how many views does it have? That's a feature that we use to actually calculate the level at which we should say something about Peter. So I'm going to wrap up this. I'm going to say that we also have, to make this work, we have boosting stuff. But basically what we're trying to do is to remove hallucination while giving you final sample guarantees on the error rate. And so we're going to try to optimize this trade-off between the utility of the output, print as much as you can, and not hallucinating too much. Now, all of this has a lot of software that goes with it. You can go and install all of this. And so thanks to John Chirian, there's a GitHub where you can install and run all of our experiments. I have to say, you have to query the ChatGPT API quite a few times. You have to expand compute power. It takes a bit of money to do this, but that's the game in town these days. I want to thank you for your attention. We have an election around the corner in the United States. A lot of people are actually, including the Washington Post, using conformal prediction to get calibrated forecasts. And so please look at your favorite newspaper to see conformal prediction in action. Thank you very much.
Thank you very much, Emmanuel. So we did start 5 to 7 minutes late, so we will take a couple of quick questions, if there are any. Yes, please.
Thanks for the talk. You said that you have calibration conditional on different kinds of groups that you mentioned. Like, are you sort of manually choosing these groups, or how do you figure out what are the different kinds of prompts?
So we do calibration based on groups, yes. And what is your question?
How are you figuring out those groups? You mentioned like toxic versus non-toxic. I don't know, famous
statisticians. Yeah, exactly.
So
for example, like we try to build groups for medical questions, the kind of questions you might ask. We use toxicity. We use the number of views, the number of, we go on the internet. We say, how popular is this topic? Is this a popular topic? Is it not a popular topic? This is a bit ad hoc, what we're doing, but we're trying to make sure that there are no corners of prompt space for which we do terribly bad. And so there's a lot of engineering in what we do. We don't have the best recipe, but we're trying to create group that makes sense.
Okay, so it's still like a manual process. You're not like sort of doing some other thing where you're like automatically figuring out what the group is.
But you are standing on the work of others. Like, and we're not the only one who classify, it's basically a clustering things, right? Like, we're not the only one classifying prompts. And so we are leveraging this thing, of course.
Thank you.
Thank you for a really interesting talk and great results. I was wondering about the exchangeability. So you can adjust using weights because you don't really think that maybe query pairs are really exchangeable, right?
Exchangeability of what here? What exchangeability?
So your underlying guarantees are either you have your exchangeable structure, which you might not have actually in real applications.
We're talking about the drugs or the prompts or?
Well, the LMMs, but possibly also the drugs. Well, for the drugs, you can adjust for the distribution shift.
So what I'm assuming for the drugs, let's say, is that I have a set of calibration drugs. They're sort of exchangeable. In fact, I'm going to say that IID from some distribution that I don't know about. I have the set of test drugs. They're also IID from a certain distribution, but these two distributions are not the same. The likelihood ratio of these two distributions is what I call the covariate shift WX.
Yeah, I'm just impressed how well it works because the IID assumption might not necessarily hold.
Yes.
Right? I don't know whether you have looked into this. So you have your weighted conformal prediction where you can adjust for non-exchangeability, but then getting the weights might be another tricky issue.
But we are. So what? the only source of non-exchangeability in the drug discovery, for example, is that the calibration drugs are actually exchangeable among themselves, the IID. The test drugs are also IIDs. And once you, so they're sort of weighted exchangeable, if you see what I'm saying. And that's all I need, really.
Okay, thanks.
Well, I'm sure there are a lot of questions that we all have, but Emmanuel will be here for the rest of the week. So let's once again thank him for this very thought-provoking lecture. Thank you very much.
On behalf of the local organizers, the gift from Ruhr University Bochum. Most of you have heard this story, that we boldly claim that Ruhr University Bochum is the only university in the world that produces its own perfume based on local research done here by Professor Hutt in the Department of Biology. Emmanuel, so that you can always remember Bochum.
Okay, welcome everybody to this second session of the day, which is the Bernoulli Laplace lecture. And it is my pleasure to introduce Professor Ji-Hong Lin from Harvard University. She's a professor and former chair of the Department of Biostatistics there. She works on statistical and machine learning methods, in particular analyzing massive and complex health data. She's worked on many different things, applied, theoretical, methodological. To just give you one example of her many pioneering research achievements, she was one of the early contributors to the analysis of COVID data on transmission, public health intervention, and epidemiological characteristics. I remember in the early days of COVID, using one of the apps that she and her collaborators developed on the web that you could track the evolution of COVID. She, of course, received many prestigious awards, and there's no way that I can mention even a small fraction on all of them, so I just picked a few. So in 2006, she received the COPS President's Award. In 2017, she received the COPS Florence Nightingale David Award, and her many recognitions culminated the last few years with two extremely major recognitions. She's been elected to the National Academy of Medicine in 2018 and to the National Academy of Sciences in 2023. She also did a lot of service for the community and for her university. She's the former chair of the COPS, the Committee of Presidents of Statistical Societies, and former member of the Committee of Applied and Theoretical Statistics of the National Academy of Science. And there are so many that I have to stop here and let her give her talk. Please join me to welcome Ji-Hong for this Laplace lecture.
And thank you so much, Aurora, for the very generous introduction, and thanks to the committee for this great honor, and it's great pleasure to be here and to deliver this lecture. And so I want to share with you some of the lessons I have learned in the last 10 years working on statistical genetics genomics. So as we all know, ChatGPT is a tipping point for AI. And so the new type of data which have arisen in the last couple of years, such as the text, images, and voices, which are not familiar to statisticians. So, and also nowadays, the data are much more complex and much more heterogeneous beyond what we are familiar with. And so the statistic also appears invisible in emerging AI opportunity, including the funding opportunities and also policy makings. And also, another limitation we have as a statistician is we have limited engineering ability. And so the other challenge we face is that the traditional statistical theory is challenged by many emergent learning methods, such as the deep learning, transformer, large language model, and the diffusion models. And also, this challenge is faced by both the statistical community and AI community in academia. In particular, the computational resources in academia is much less compared to industry. So for example, think about Meta, it has over 350,000 GPU. At Harvard, we only have a couple hundred GPU. So then we ask ourselves, and how can statisticians position ourselves? And in the age of AI, in particular, how can we have a visible seat at the AI table? So basically, this is a two-way street. One is that it's useful to leverage transformative AI potential and in statistical science. In the same time, it's important to enhance the trustworthy AI by infusing statistical principles and also thinkings and in the AI. So this talk is organized in several parts through several takeaways. The first takeaway I learned is it's important for us to be open-minded and stay curious and think out of the box and also willing to take the risk. So use the ChatGPT large language model as example. So as we all know nowadays that the number of ChatGPT parameters are huge. And like 4, it has a trillion parameters. So when ChatGPT just came out 1.5 years ago in December 2022, my first reaction was, how can this work? And it seemed like overfitting. And but the AI and the engineer's mindset is very different. So make it work first, and based on the empirical evidence, and then figure out why. And then later on, and I learned this really interesting phenomenon called carbon descent phenomenon. Multiple people in the room are familiar with this. So the statisticians are familiar with the phenomenon on the left-hand side of this blue line. And so that indicates like if the red curve is a testing arrow, the training arrow. So when the number parameter goes up, the training arrow goes to 0, is overfitting. And so therefore, one use the testing arrow. So when the number parameter goes up, but not too big, and then there is a bias variance trade-off, and then the prediction arrow goes down, but when the number parameter goes up, and then the overfitting problem. And but if the one move beyond this traditional phenomenon, if when we consider extremely large model, and there's this interesting double descent phenomenon when the model became extremely big, like in the large language model, and then the prediction error becomes smaller, it's more likely the true model is within this model space. And so my colleague, Pragar Sir, also told me there are a few earlier papers than this 2023 paper, and looking at this double descent phenomenon. So this tells us it's important for us to stay out of our comfortable zone and really cultivate engineering and CS mindset, and also they learn from the engineering mindset, they learn from the trials. And so it's important to learn from empirical research, and then go to the theory, understand the empirical research. This also tells us that it would be good for us to think about disruptive statistical inference, and in particular, developing non-traditional statistical theory for many emergent learning methods, like the transformer, large language model, and diffusion models. And in particular, and we have to ask ourselves, what can we bring as a statistician to that AI table? Something people care. Definitely answer is, as a statistician, a natural answer is trustworthy AI, in particular account for uncertainty, like Manu gave a fantastic talk about this. But the question is how? And then how can we make people care about what we do as a statistician? So first of all, so if one thinks about traditionally, we are interested in statistical inference, like hypothesis testing and estimation. But are we really interested in making inference about this 1 trillion parameter in large language model? The answer is probably not. Then generally, we are interested in some kind of population parameter. Then how can we connect the population parameter with those trillion parameters? Those are the working models. And also, how can we define the population? While listening to Manu's talk, I even asked myself whether we really care about population parameter, and whether hypothesis testing should be framed as a population parameter. So this is really not a traditional thinking. And also, we have to ask the even very basic question, what are the data? And so nowadays, like text, video, and voice from internet, there are many, many different type of data we are not familiar with, and also there are no sampling frame. Generally, we are comfortable with the sampling frame. And furthermore, and should those synthetic data and augmented data generated from the generative model that are used to have a better learning for the features, should they be considered as the data? And also, we ask ourselves, what really do we mean by models? And so nowadays, the model is much more broader and also are implicit. For example, for transformer, it's difficult to write down the model explicitly. And so the model parameters may not be of interest, like those 20 trillion parameters in the large language model, and also population parameter may not be in the model, and even the people may be interested not just formulating the model in terms of population parameters. And also feature space. Generally, we are comfortable with pre-specifying the feature space. If, for example, in the Hilbert space. But nowadays, the feature space may be unspecified, and it needs to be self-learned. And to illustrate the last point about the unspecified feature space, let's look at the traditional machine learning and the representation learning. Traditional machine learning basically manually pre-specifies the feature space. For example, linear feature space, quadratic feature space, spline space, radial basis, or kernel space, and through feature engineering. So now, for example, like random forest, the feature space is the trees. And the kernel machines, a linear kernel, the features are linear basis. And the Gaussian kernel, the features are radial basis. So we basically specify some kind of feature space up front using some Hilbert space. And by representation learning, and think about it differently, it extracts useful feature automatically and without specifying any kind of functional space. So if one look at the deep learning, it is a special case of representation learning and using the neural network through many layers to learn representation of the data. So for example, if you look at the traditional machine learning, and so basically one extract the feature manually and specify some kind of pre-specified feature space. But now if one think about representation learning, so basically one use the data to learn the feature space without pre-specifying the feature space. So this is kind of different from what we are trained for. So if one think about a formulation, so think about input the data, and then think about there's some kind of true generative model as a function of the feature. Traditionally, we specify the feature in some kind of functional space, like Hilbert space, or kernel space, or spline space. But now, with the representation learning, basically one define the feature using data-driven feature automatically without pre-specifying the functional space. And the feature can be used for downstream task learning. So this is the takeaway number 2. I work on statistical genetic genomics, and so one thing I learned is important to be a full data scientist. What do we mean by that? So one needs to think about the data science ecosystem. So this is how I think about it. And the data science ecosystem, I think about 3 pillars. One is the diverse and fair data. Second is the statistic, machine learning, and AI method, tools, and also infrastructure. The third is the data analysis and also the result interpretability. So in order to build this functional to make effective data science ecosystem, so it's important that we as a statistician become a full data scientist, not only know the statistic and the computing, but also know the domain science. In my field will be the genetics and genomics. And also, traditionally, we were taught in graduate school it's important to communicate with the domain scientist. And so nowadays, we need to learn how to communicate with the computer scientists as well. And we have not really understand the computer science, the culture in order to communicate with them effectively. So it's good to be partner with them, but not to compete with the AI community. So in order to really for people to work together, it would be good to think about how we can work together to make impact in science by solving real-world big problems and answer important questions. So I learned in the last 5 to 10 years, and by working with a large genetic data, data fairness outweighs the data size. So data size right now is not an issue. And for big data, the bias is much more important than the variance. And so increased data fairness and diversity is critically important. To illustrate, I'm going to use the whole genome-wide association study. In the last 10 or 20 years, tens of thousands of genetic variants have been identified associated with the human diseases, and such as heart disease, lung cancer. And so the traditional GWAS study basically genotype billions of common genetic variants across the genome. For example, like the 100,000 lung cancer cases, 100,000 controls, and then scan the genome one SNP at a time and create this Manhattan plot and identify which genetic variants associated with the human diseases, such as lung cancer. However, 86% of the GWAS samples are from European. This results in health disparity in this genetic research. If you look at this figure, and the right part corresponds to the sample size of the European, and the blue corresponds to East Asian, African correspond to the purple. So you can see that over time, and this is consistent pattern, majority of the sample come from the European. And so what is the problem? So if one look at the polygenic risk score, and so polygenic risk score basically aggregate the genetic information across the genome and create a risk score to predict disease risk for cancer or heart disease, and then develop disease risk stratification. So for example, one uses GWAS summary statistics and then use that to calculate the SNP weight, basically the beta hat. Suppose generally there's millions of beta hat and from the associated with the SNP. And suppose a new patient come in and then genotype that person, got that person's genotype, and then calculate this person's polygenic risk score that basically X transpose beta. And then use that to predict this person's risk. So many of the GWAS data, individual level data, are not publicly available, but the summary statistics are widely available. For example, from the GWAS catalog and also the dbGaP. What is the problem? So if one look at the figure on the left, so you can see that if one uses the DAT as the polygenic risk score from the European as a reference, and you apply the SNP weight, the beta hat, calculated from European, applied to other minority population. For example, the East Asian will be the blue, and you can see the accuracy is only 50%, and the African is purple, accuracy is 25%. So that indicates there's an important data fairness, that if you use the GWAS sample, most of them come from European, apply that to East Asian and African, the prediction performance will be terrible. This also indicates the importance of algorithm fairness. So therefore, transferred learning is particularly important in developing polygenic risk score. And another question people usually ask is, given the large number of SNP across the genome, millions of common SNP across the genome, and the traditional method uses the linear model, for example, use the penalized likelihood. And so can the deep learning help improve those kind of linear model? And a good number of people have tried using the deep learning to construct polygenic risk score, but the results are not promising. So the natural question is why? And it is a powerful method, why it doesn't work well, and for a polygenic risk score to predict the disease risk using the genetic profile. The answer is, from my perspective, is the GWAS signal generally are weak, are mainly linear. And to show you, so if one look at the autoencoder, so it has both an encoder and a decoder. The encoder basically represents the data using the representation learning and through some kind of representation space, and decoder regenerates the data. So the most classical convolutionary neural network is this few-word neural network. Think about this, only 3 layers here. The input is a SNP. And then you create that activation function, which is the function of the input data X. And then the W statistician called regression coefficient, and machine learning field called the weight. And B we call intercept, they call the bias. And so you can see this F function is activation function. Generally in deep learning, and F is a nonlinear function. Now, so if you move to the second layer, you put A1 as an input, and then learn the W and the B again, and then you can see this basically is a convolution. And so if F is linear, you can see we don't need this convolution. Linear applied to linear, still linear. And so therefore, what it tells us, if the effects are really linear and also there's effects at no interactions, and so seen in a deep network, and not necessary. And in GWAS study, because the signals are weak, and so therefore those kind of fancy method is not that better than the simpler method. So what is generally those kind of deep learning methods are useful when the signal are strong, like in images, and also the signal are nonlinear. So what this tells us is we should know the domain size, and before spending too much time trying the fancy method, and then by the end, it doesn't improve over the simpler method. So takeaway number 3 is many of the individual level data are not publicly available. However, summary statistics are publicly available. It will be useful to fully leverage the summary statistics for more advanced analysis. And to illustrate the point, I'm going to use the GWAS study. And so the GWAS data, because of confidentiality reason, individual level data, such as UK Biobank data, are not publicly available, and one can only do the analysis in the cloud. And so, however, the GWAS summary statistics are publicly available. So the most simpler summary statistic is X transpose Y, X transpose X. In genetics, X transpose X is called the LD linkage disequilibrium. A natural question we ask ourselves, what can we use those summary statistics, X transpose X, X transpose Y, and beyond linear regression, and also meta-analysis? We know for meta-analysis, for linear regression, if I know X transpose X, X transpose Y, I can do those. Can we go something more complex model, but with only those 2 summary statistics? And the answer is yes. I'm going to illustrate using 2 examples. The first example is the linear mixed model. So if we know the linear mixed model, and so that basically the simplest model is in genetics is written Y is equal to X beta. And so we assume beta follow a normal distribution with mean 0 variance sigma g squared, and epsilon follow a normal distribution with mean 0 sigma e squared. X generally is the millionth SNP in genetic study. And so in genetics, generally one is interested in calculating genetic heritability. That basically is a sigma g squared divided by the total variance of Y. So for height, heritability is about 80%. That means it's highly heritable. And also this is also called a signal-to-noise ratio. The natural question is, traditionally, when one estimates heritability, one fits the mixed model, like what I wrote down up here, and fit the RAMO. And so if you look at the RAMO likelihood, you can see that it's not obvious how one can calculate the variance component by maximizing this RAMO likelihood with only the not individual level data, but with only 2 summary statistics, X transpose X and X transpose Y. Can we calculate the heritability? The answer is yes. It turns out it's a happy ending. By doing some algebra, you can show that blob estimator can be iteratively estimated using the X transpose Y, that is a score statistic, and also LD matrix, that X transpose X. And then you can calculate sigma g squared and sigma e squared. So that is very nice. I don't need to do individual level data. I can fit the mixed model just using the 2 summary statistics, which can be publicly available. And so this paper was published in Nature Communication last year. The second example is people are all familiar with the penalized likelihood. So for penalized likelihood, that can be used to construct polygenic risk score. Traditionally, we know to compute penalized likelihood, like lasso or the elastic net, one need to use the individual level data. So here I focus on the L0 learn. So that basically is L0 penalty plus L2 penalty, the same result applied to the lasso as well. And so the natural question we ask ourselves is, suppose I only know X transpose X and X transpose Y without individual level data, can I calculate my beta hat through this penalized likelihood? And we call this all sum. The answer is yes. And the paper just appeared in PNAS 2 days ago, and also was selected as a PNAS showcase. So in particular, by doing simple algebra, you can show that, so here you can see there are 2 tuning parameters, lambda 0, lambda 2. So given those 2 tuning parameters, lambda 0, lambda 2, and one can easily show, and one can calculate those penalized likelihood estimator intuitively through this coordinate descent algorithm. And so we should only rely on the summary statistic X transpose X and X transpose Y without knowing the individual level data. You can see the thresholding, and also you can see the shrinkage that only depends on the summary statistic. So that is very good. And the second question we ask ourselves is, traditionally, when we estimate the tuning parameter, we do the grid search. In particular, we have a tuning data set. We select a grid of lambdas, find out which grid gave me the smallest prediction error, and use that as the tuning parameter. Is this optimal strategy? And we found that is not optimal. And this ensemble strategy works better. In particular, suppose I have a grid of lambdas, 1,000 grid of lambda. For each grid, I have a beta hat. Beta hat, this is a million beta hat. And I do the 1,000 beta hat. This is a million by 1,000 matrix. And now, so I have a tuning data, Y and X. And then after I calculate this 1,000 beta hat set, then I calculate the predicted value using this 1,000 beta hat using different grid. And then I suppose I do the penalized likelihood. Then I calculate the new beta hat. And this new beta hat is the linear combination of those grid searched beta hat. And this basically is ensemble estimator. And we found that this is better than the grid search estimator. Why is that? The reason is one can do a simple algebra. One can show that by doing this kind of ensemble estimator, 200,000 samples, and only one person have that variance. And about 16% are doubleton, that means only 2 people have that variance. So therefore, scalability is critically important to us when we analyze such huge data. So what is the goal? The goal is we want to scan the genome, identify the genetic variants, and associate with the human diseases, such as heart disease and lipid. And so because the variants are so rare, so we have to group them into the mask with the SNP set. Then this basically will require domain knowledge. To this end, so the first thing we need to do is annotation. Annotation is a huge effort. Not everybody is willing to do this, but it's critically important. And so through the whole genome sequencing program, NHGRI, and we led this annotation of the whole genome. Across the genome, totally there are about 3 billion variants across the genome. And at each position, there's 1 reference allele, 3 alternate alleles. So totally there are 9 billion variants. So this annotation database is a relational database, has 9 billion variants. And we have currently has 300 annotation, including RENCODE, roadmap, and GTAG, and so on. So this is a huge database. And so the query had to be extremely fast. So that's why we built this PostgreSQL relational database through efficient indexing. One search for one particular variance, one can find it in 1 second. And so this includes allele frequency, conservation, protein function, epigenetic function. People have heard about alpha missense, for example, developed by the Google DeepMind. And it's basically annotation of missense variants. And so it's, then the epigenetic come from the ENCODE. And we make this database fully publicly available and to the community. Not everybody is a statistical geneticists or computation biologists. To increase the user experience, we also build this Fever GPT. This is a large language model interface of this backend Fever database, and build it through the ChatGPT API. We built through a Fever API. And so this led by my computational biologist and also software engineer. So basically, people know how to do the ChatGPT to do a query. And so what we do is one specify a query, for example, provide functional information of this particular variance, and then one uses backend database we built, and the 9 billion variance the database, and then summarize the information of the functionality of this variance. It can also do some calculation. For example, BRCA1, we all know this is a gene associated with breast cancer. If one asks how many pathogenic variants of BRCA1, and basically pathogenic variant, this variant means very functional. If one has that particular mutation, it basically the person is very likely to have breast cancer. And then it does then it calculates there are 96 pathogenic variants used in this database. And also, in order to build this data science ecosystem, and it has to be cloud-based. And so the traditional way for the data sharing is data copy. Basically, copy the data to the individual cluster. I make a copy, and to the UK Biobank data, to Harvard cluster, Aurora make a copy to her institution. So basically, no data sharing. This model is not sustainable, and because the whole genome sequencing data are very big, and it's too costly to save the data to your own cluster and pay the egress and the data transfer cost. So now the model is bring the researcher to the data, to the cloud, for example, and multiple cloud systems, such as Google Cloud, Amazon Cloud, and one need to be familiar with the workflow description language and workspace. And so they are the multiple existing ecosystem. For example, alphas data and the genome sequencing data are only available in Anvil, and the TopMed data are only available in Biodata Catalyst by NHLBI, and UK Biobank data cannot be downloaded anymore, and it is only available in RAP, this powered by DNA nucleus. So because cloud sounds wonderful, but it's costly and easily can break the bank. So therefore, scalability is critically important to us when we develop the method. First of all, we need to think about data storage. And so if one think about a UK Biobank and the whole genome sequencing data, for example, 200,000 whole genome sequencing data on the RAP, and it has the over 60,000 files and stored in the traditional file format, VCF format, is a couple hundred terabytes. 1 terabyte in Google Cloud costs $300. So that's why even you don't do anything, just store the data, it can break your bank. So the first thing we need to do is to create a data format that is scalable. And so we create this called, we annotate the GDS format, putting the annotation data and the genome data from the UK Biobank in one data file. And so this compression rate is very, very high, of over 1,000 times. And so this makes it much, much more cost-effective, and then one can easily push it for downstream analysis. And we make this available for the UK Biobank community and TopMed community as well. And now, in order to do the analysis, we want to automate everything. This completely automated analytic pipeline. So if one provides the whole genome sequencing data, one provides the ERChart data from UK Biobank, then everything is automated. So we have this backend database, this Fever functional annotation database with 9 billion variants in the cloud ecosystem, like in Anvil, Biodata Catalyst, and also UKB RAP. And then one first run the QC, and through the Hill, this is a cloud environment, a cloud pipeline as well, developed by my colleague at Broad. And then one run this Fever annotator developed by my lab to annotate any whole genome sequencing data. and so create this functional annotated whole genome sequencing data. And so one may wonder why we want to create this 9 billion variants annotation database. For UK Biobank, it's 1 billion variants. For TopMed, it's 1 billion variants. The reason is for different study, the observed variants are different. And so therefore, we want to create this backend database that can be used to annotate any whole genome sequencing study. Then after we create annotated whole genome sequencing data with this GDS format, this used for gaming, and then we can run this star pipeline developed by my lab to analyze the whole genome sequencing data at scale. And so I'll show you the cost of this. So you can see the whole thing is end-to-end, and so completely automated. And in order to make the analysis method and result useful, and it's important to develop scalable and interpretable statistical machine learning method by incorporating the domain knowledge. I'll use the whole genome sequencing analysis method for real-world analysis as an example. So how to incorporate functional annotation in the real-world association test. And so we developed this star and the star pipeline. This co-led by my 2 former students, and the paper was published 2 in Nature Genetics and 1 in Nature Method. I think important for statisticians published not only in statistical journal, but also in Nature Science and also Cell as well. They publish method paper, but the writing style is very different. So the main idea is to empower real-world association test by incorporating multifaceted functional annotation from this functional annotation database we built, Favor. So how to do this? And so in GWAS study, basically one analyze 1 SNP at a time. But when we deal with a whole genome sequencing study, because the variants are too rare, we cannot analyze 1 SNP at a time. We have to analyze a mask at a time. And so how can one define the mask? And basically, this needs the genomics information. So for example, if you look at the functional category called the enhancer of ApoE that regulates the gene. And suppose there are 100 variants of ApoE enhancers, and suppose the phenotype is LDL, this is bad cholesterol, lower is better. And so we want to see whether this 100 variants associated with LDL. So if I know among those 100 variants, only 4 variants, beta not equal to 0, I want to do 4-degree freedom test instead of 100-degree freedom test. But in reality, I don't know there are 4, I don't know where they are. So this oracle strategy does not work. But I also don't want to do the 100-degree freedom test and to test whether there's association of the enhancer of ApoE with LDL. So suppose I have this marginal score statistic, 100 marginal score statistic. How can I aggregate those 100 marginal score statistics? And to do that, first one need to create the mask, and so based on the functional information. So through the coding region, group them into lost functional variants, missense variants, synonymous variants. In the non-coding region, group them into the promoter, enhancer, and overlaid with CAGE and DHS. One can also do the sliding window approach, do the fixed window size or dynamic window size. But when one analyzes the non-coding region, one need to do a little bit more. And because the non-coding variants are functionality are cell and tissue specific, this also asks for integration of the single cell data and the CRISPR data as well. And now, the goal, as you recall, I want to see whether the ApoE enhancer is associated with LDL. There are 100 variants in the ApoE enhancer. There are 100 score statistics. How can I aggregate those 100 score statistics? About 10 years ago, and the 2 methods were popular. One is were developed. One is called the burden. And the burden basically is a linear combination of those 100 score statistics with the weight. So if I know there are 4 betas not equal to 0, I would put weight 1, and for those 4 beta and 0 for the others. But in reality, I don't know there are 4. I don't know where they are. So this weight, oracle weight, doesn't work. And so this method generally works when the beta are in the same direction because this is a linear combination of the score. And for lost functional variants, this will work well. Another method called SCAD, and we developed about 12 years ago and used the kernel machine framework. And then use a different kernel. Then later on we realized that a linear kernel works the best in this in genetic setting. And basically, it turns out this can be written as a quadratic function under the score statistic, much simpler form. And so you can see if the signal are in different direction, because the score statistic are quadratic and squared, so the signal don't cancel out. So this works well in the non-coding regions. And because we don't know what weight to use, we have many different functional notation, but which weight to use? I can use conservation as a way to calculate the scat statistic at a p-value. I can also use the epigenetic as a way to calculate the scat p-value, but which weight to use? And so that's why we need to combine the test with a different weight. And because those different tests apply to the same data, those p-values are correlated. So this method was developed by my former postdoc, Yao Liu. It's a really beautiful method. It's a Cauchy combination method. It's a powerful method to combine correlated p-value. So basically, you do a time transformation of the p-value, and then you sum them up. And so after you do the time transformation, it becomes a Cauchy distribution. And because this, if you try the different weight, find out which p-value gives you the smallest p-value, report that one, or use the minimum p-value and as a test statistic, and generally that is cheating. And but in order to figure out the minimum p-value distribution is complicated because you need to account for the correlation. But using this Cauchy combination method, in the tail, you don't need to worry about the correlation. So this is really convenient. So I can use a different annotation as a weight and then combine the test using this ACAT method. So basically, this provides an overview of the p-value combination method, the traditional method, the Fisher method. So basically, you do have a p-value, take a log transformation, and then combine them. And this will follow a chi-square distribution if the p-value are independent. But if the p-value are correlated, this distribution is complicated. For the ACAT method, and so when I use a Cauchy method, and so we don't like Cauchy, it doesn't have a mean, doesn't have a variance, it has a heavy tail. But because this heavy tail has a beautiful property, and so if the p-value are independent, then you combine them through this Cauchy test, it still follow a Cauchy. But when the p-value are correlated in the tail, and it still follow a Cauchy, no matter what correlation you have. So this is really, really convenient. In many situations, we don't know there's a UMP test. So basically, now we have this star pipeline. You read in the data, and we use a favorite annotator to annotate the whole genome, and then we use different annotation, and as a weight, apply the burden or the scat test, and then use ACAT to combine them. This creates, by the end, the p-value of the association of ApoE enhancer and LDL. So this is completely automated. So this work was published in the Nature Genetics and Nature Method. Another thing I want to mention is scalability is critically important. So we need to make it scalable, and in RAP, in UK Biobank's cloud platform, everybody can afford. So to annotate the whole genome with 1 billion variants in UK Biobank, it only costs $25. And to fit the null model, 25 cents. To scan the whole genome for LDL, only $25. So therefore, for annotating the whole genome, you only do it once. But when you analyze every phenotype of the EHR data, it only costs $25. So this is very, very scalable. So this is the real variance takeaway. So we developed a favor GPT to provide a comprehensive whole genome variance functional annotation database of 3 billion positions, 9 billion variants. And the favor annotator can be used to annotate any whole genome sequencing studies, such as UK Biobank, ALPHAS, and TalkMed, and dynamically incorporating multiple functional annotation, then start boost the power of the real variance association test. So this is the last part. And so I want to talk about ensemble inference. So in particular, ensemble is a good thing. So how can we move from ensemble prediction to ensemble inference? So this work was motivated by this reference association test. So we developed this SCAT method about 12 years ago. And this is widely used in whole genome sequencing study nowadays. We ask ourselves, 10 years later, is this the best method we can do? The answer is no. And so this paper published in GISB earlier this year. So in particular, one asks, is the burden test the best test if we assume all the beta in the same direction? The answer is no, because the burden test assumes all the beta to be the same. So how can we develop a powerful test? Null hypothesis is 100 beta equal to 0, alternative is beta greater than 0. And this will require constrained MLE. You can do this when the dimension is 203, but when the dimension is 100 or 1,000, it's very difficult to do this. And scalability, as you recall, is very important to us. So what can we do? So let's talk about ensemble prediction. The most classical ensemble prediction is random forest. So basically, one build a tree, do a bootstrap sample 1,000 times. For each bootstrap sample, you build a tree. After you build a tree, what you do is you use the, suppose you have 100 variables, and you take a square root of 100, you have 10. Each time you build a tree, use 10 variables. And the reason you want to do 10 variables instead of 100 variables for each tree is if you want to make the tree independent. So therefore, the variance of the prediction will be small. After you build this 1,000 tree, you average them. This basically is random forest. So random forest is better than bagging. Why? The reason is bagging use M equal to P, use 100 variable. So the tree are all correlated, and then the prediction variance is too big. And the question we ask ourselves is, we are not interested in prediction in this situation. We are interested in testing. We are interested in whether a particular variance functional category and associated with LDL or cardiovascular disease. So given the success of ensemble prediction, how can we develop an ensemble method for inference? In particular, hypothesis testing. How can we move from ensemble prediction to ensemble testing? So let's start from ensemble learning, random forest. So random forest, what we do is we build a bunch of weak learners, and those are the trees. And the trees are weak learners. We do that 1,000 times. And for each tree, we build a prediction model. And then after that, we average those 1,000 trees. That basically become a strong learner, that is random forest. And then we are not interested in prediction. We are interested in testing. Then you can see what we can do is replace the base learner by base testing, and then replace ensemble learner by ensemble test. But the question is, what can we do with base test? What can we do with ensemble test? So we are going to introduce random weight in the base test to construct the base test. And for each base test, we can apply the different base test to the same data set. And then we do that 1,000 times. But the problem is, when we do that, those 1,000 p-value, because they are applied to the same data set, those 1,000 p-value are correlated. How do we ensemble them? Because most of those random weights are likely to be wrong, and many of those p-value are likely to be large. So therefore, averaging the p-value, like what we do in random forest, is not a good idea. So what we are going to do is we are going to ensemble them using the ACAT. As long as some of the random weight is the true signal direction, and then the ACAT basically very similar to the minimum p test, but automatically account for correlation, then that will give me the result very similar to the Oracle test. And to illustrate, let's focus on the burden test. The Oracle test, suppose I tell you the true beta. Then the Oracle test, this is the UMP test. Basically, you project your score statistic, 100-dimensional score statistic, to the true beta. So that is basically represented by this red line. This is true beta direction. This is Oracle test. In reality, we don't know the true Oracle direction, true beta direction. The burden test basically assumes all the beta to be the same. That is a 45-degree line. If the 45-degree line is a true signal direction, then the burden test will be the best. However, in reality, the true signal direction is unknown. Most of the time, it's not the 45-degree line. What can we do? That basically is ensemble testing. So basically what we do, we generate a bunch of random direction in the first quadrant. will project the score statistic to those random directions. As long as one or two of those random directions close to the true signal direction. So basically, one or two of those green directions close to the true signal direction. We ensemble them using the ACAT. That will give me the result very similar to the Oracle test. So that basically, you can see the idea is very simple and very convenient, very scalable. And so we have generated a bunch of random directions in the first quadrant and then project the score statistic to those random directions. And we do that 1,000 times. Then we got 1,000 p-value. Most of those green directions, random directions, are likely to be wrong. And so most of the p-value are likely to be big. But as long as I have a small number of random directions close, the green direction close to the red direction, the p-value is likely to be small. And when I do the ACAT Cauchy combination, it's likely to be very close to the smallest, the direction with the smallest p-value. But automatically account for the multiple look of the data and also account for the correlation among the multiple tests. And so basically, how to generate the random direction? We generate the z from normal 0, 1, standardize it. That will become the polar system. And then we ensemble them using the ACAT. That basically gave me the final ensemble test. To account for the annotation, and we can change the z distribution to normal 0, A. A is annotation, and then this will give me the result and accounting for the annotation. So apply this to the Eric whole genome sequencing data. You can see if I do the burden test versus I do ensemble burden, you can see the number of discovery almost increased by 10 times. So we can do the same thing for the SCAT. If we do the SCAT versus ensemble SCAT, you can see the number of discovery increases by 50%. So that is very encouraging. So to summarize this part, an ensemble test is a flexible and robust way to boost the power of the weak base test, and it introduces random weight through the random projection to create the base test and ensemble them using the ACAT. This is a powerful method to combine the correlated p-value. And so this is the final remarks. So it's important for us to be open-minded and take risks when embracing AI in statistical research, education, journal, and conferences. And and also improve the data and algorithm fairness. And so in particular, the data fairness will require study design. So the statisticians are important to help with a good study design. And also be a full data scientist. And so by building a scalable end-to-end data science ecosystem using statistics, machine learning, and AI and domain science, and also integrate domain science in statistics, machine learning, and AI method to make the result interpretable. And also, the ultimate goal is to prioritize scientific impact and working forward and together with the computer science and the machine learning community and the AI community and the domain scientists. Thank you.
Thanks for this absolutely fascinating talk, full of lots of very, very interesting takeaway messages. So, are there questions in the audience? Yes?
Thank you for the interesting talk. My background is computer science engineering, so indeed I like to make it work. So my question is regarding these neural networks. Given the high sensitivity of neural networks towards this architecture, so if I want to learn the representation of my feature space given any data, so for n number of neural network architectures, I'll have n number of feature representations. So from that set, how do I know what is the best or rather correct representation, or even the best or correct representation lies within that n number of representations at all? So how do I know that?
Yeah, so I think that's a great I think that is a great point. So one thing I feel is it's very important for us to keep minded and also learn from other fields. And so that will help us to think about those lines.
Thank you.
Yeah.
Thank you. Just a small question also for the previous speaker, Professor Candace. What is the role, say, for the LLM? There are now, I think, even central limit theorems and probability theory. What is the role in general for the data science developments of central limit theorems, of probability theory, of more classical statistical theory? Thanks.
I cannot hear very well.
Sorry, I didn't understand the question.
So you were talking about
The
ensemble
sound
tests.
is the sound. I don't think we're going.
You were talking about ensemble tests, but there is naturally also asymptotics. Do you hear me? Do you hear me?
It got cut. It looked like the mic got cut. Cannot hear very well.
So the question is about the role of probability theory asymptotics for the tests in say ensemble tests or exactly probability or classical theory.
Come here, I cannot hear. Oh, yeah. Okay. The asymptotic theory is in the ACAD method, the Cauchy combination method. The theory is in the JASA paper, and that was published in 2020. Yep. I think that basically the trick is that because the Cauchy has a very heavy tail, and so that really help. And because in the heavy tail, and the behavior just different from the normal tail. So that's why even the tests are correlated, in the tail still follow a Cauchy.
Okay, so because in the interest of time, and also because here we really understand very poorly the questions, I think if there are more questions, I invite you to approach Jihong during the coffee break and join me to thank Jihong again for this fascinating talk.
Thank you.
No, it's on. Okay. Okay, so, okay. A very warm welcome from my side to the World Lecture. So it is my pleasure to introduce, as we say in Germany, Professor Dr. Peter Lukas Buhlmann. So actually, Peter does not really need an introduction, but I will nevertheless try to summarize in a few words an immense research career. So the research of Peter spans statistics, machine learning, computational biology, and medicine. And in fact, he has the rare ability to simultaneously develop cutting-edge new theoretical results, while also contributing importantly to modern applications. A particular focus of his research is on high-dimensional statistics and more recently causality. So I will come to this a little bit later. So career-wise, Peter is now a professor at the ETH Zurich since 1997 and full professor since 2004, after a passage at UC Berkeley and studies in the ETH. It's absolutely impossible to give an exhaustive list of his achievements, community service, and honors in such a short time as for introducing him. So I will just say a few points. Starting with the IMS, because we are in an IMS setting. So Peter was a president for the last term of the IMS, and is currently an IMS fellow, an ASA fellow, an EC elected member, and also member, since we are in Germany, of the German Science Academy, the Leopoldina. More generally, he is in several boards and committees of many research centers, and has been serving as editor and associate editors in many very prestigious venues. For instance, currently he's a co-editor of Springer series and lecture notes in statistics, and he was an editor of the Annals of Statistics. He has won several prestigious prizes and given several very prestigious lectures. I will just mention here the Guy Medal in silver from the Royal Statistical Society, and the ERC Advanced Grant. And regarding lectures, what is really impressive, I think, is that he has given most prestigious lectures in a very vast diversity of venues, either in general mathematics, like for instance in front of the ICM, but also in more applied settings, for instance in front of the Biometric Society. For lectures in stats, of course, there he has done more than I can cite here. For instance, he was a Rothschild lecturer, he gave the Chalice lecture, the Hartington lecture, the Niemann lecture, etc. Last but not least, he supervised many very successful PhD students and postdocs, and he even won for that the Golden Tricycle Award, as I read on his CV, for most family-friendly advisor. Back to his work. So Peter heavily contributing to the foundation of modern high-dimensional statistics, which is highlighted by his joint books with Sarah van de Geer on statistics for high-dimensional data, which is now a reference book for many of us on this topic. And he has particularly contributed on variable selection, which is key for interpretable statistics and machine learning. Variable selection is also a central piece of causality, which is another topic on which Peter Buhlmann is a leading expert. But I will leave for this the word to Peter, who will talk about it much better than me. So thanks a lot, Peter, again, for giving the World Lecture.
So, thank you very much, Alexandra, for this kind and nice introduction. I feel deeply honored to receive this award and having also the opportunity to present the 2024 World Lecture. I will say a few more words of thanks a bit later, but I would like to start with, and well, so I think I need your help again. So why does it just not? No, it's this one. Let me just try. Yeah? Okay. I would first like to start with this phrase, in honor of Abraham Wald. This is actually one purpose of the lecture. This is a lecture created in honor of Abraham Wald. Wald, and I pronounce this in German, was born in 1902 in Cluj, now Romania. At that time, it was part of the Austro-Hungarian Empire. He received a PhD in mathematics from Vienna University. He was advised by Karl Menger, who was also, besides being a mathematician, Menger was a member of the famous Wiener Kreis, the Vienna Circle, and that Vienna Circle actually advanced a lot logical empiricism. Why am I mentioning this? This is fairly close, maybe, to statistical inference. So later, Wald found no employment in academia and mathematics due to anti-Semitic discrimination, but famous economists in Austria, Karl Schlesinger and Oskar Morgenstern, they put his skills to work, they employed him, and Wald started to work actually in economics. In 1938, there was the Anschluss Österreich. This was the annexation of Austria into the German Reich. Menger, Morgenstern, and later Wald emigrated to the US. Because Wald had already a bit this exposure to economics, Wald came to Albert Cowles and his famous institute in economics at the University of Chicago. In the same year, in 1938, Wald got an invitation for a longer visit to Columbia University, and there, apparently, Harold Hotelling got him very interested in statistics. In 1941, Wald joined officially the faculty at Columbia University. Abraham Wald is viewed as the founder of statistical decision theory. During World War II, Wald was a member of the famous statistical research group, the SRG, at Columbia University. This was intelligence during World War II. He pioneered sequential tests and methods for quality control in defense industry. Wald is also credited with identifying survivorship bias. This is a term which was phrased already by the Romans, but what is it? What the problem was, you see here an airplane, and you see the red dots on the airplane, and these are the bullet holes when the airplane returned back to the base in World War II. And the question was, where should you put more armor to make this airplane stronger against the enemy? And Wald might have said, always look where the bullet holes aren't, because that's an airplane which returned back to the base, all others were shot. So you'd better put more armor on the engines in front and towards the rear of the airplane, and apparently that saved many US planes during World War II. In 1948, Wald became the 12th president of the IMS. In 1950, he gave a plenary talk at the International Congress of Mathematicians on the topic Basic Ideas of a General Theory of Statistical Decision Rules. Also in 1950, much too early at the age of 48 years, Abraham Wald and his wife died tragically in an airplane accident in India during an extensive lecture tour. Okay, before I move on to my lecture, I would like to say thanks. I would like to thank my teachers from whom I learned a lot. Hans-Rudi Künsch, my doctoral advisor, who's here, and Peter Bickel, my postdoc mentor. From both of them, I learned a tremendous amount of statistics, statistical thinking, and also about academic life. I would also like to acknowledge my main collaborators over many years, being you, Sarah van der Geer, Nikolai Mainshausen, Jonas Peters, From all of them, I learned a lot and benefited a lot. Thank you very much. So here is my lecture, the 2024 World Lecture. It's not lectures, you may have wondered, it's only one lecture. I decided to give only one lecture because I wanted to give more time allocation to other talks in this conference, especially to the younger generation. Before I go to the topic of my lecture, let me further acknowledge the main collaborators on the research which I'm covering here today. This is Dominik Rothenhäusler, Niklas Pfister, who's here, Armin Taib, who is here, Xinwei Shen, who is here, Alexander Hensi, and Malte Longin. This is the title of my lecture, Causality-Inspired Machine Learning. And I aim to put across maybe one idea in different facets, namely the idea of causality-inspired invariance. This has different connections and applications from applied interdisciplinary problems to statistics, machine learning, data science. And let me make this concrete. So this is my running example just for this lecture. We use this idea in other settings. It's prediction in intensive care units. This is what many people work on in machine learning. And concretely, the kind of data which we have is multi-source training data. We have approximately 200,000 samples from 200 different hospitals. This is from the US. This is the EICU database. And the goal is prediction on a new other large hospital out of the 200. This is the MIMIC3 database. This is a hospital in Boston. And the problem in a way is, okay, how well can you predict in the hospital in Boston with zero or only few samples made available? So people call this problem domain adaptation. This is a topic which is well studied, especially in computer vision. This here is domain adaptation or trying to do domain adaptation in a medical context. Maybe I just go like, even that doesn't work. Is it because I'm staying too long on this slide?
It's just a problem with the reader, I think.
This one. Okay. So we want to do domain adaptation, and what I will try to explain and cover in the talk is that we will be able to learn and extract information from heterogeneous databases like these 200 different hospitals, which is worth about 1,000 samples from the target hospital. So that's the currency. So the information value which we extract for our particular problem will be worth about if I would have 1,000 samples in my Boston hospital, and I will explain this a bit more. So obviously, this ICU prediction problem is about domain adaptation. The target hospital of interest has a different data generating distribution than in the training database. Now, in general, this is a very ill-posed problem, but of course, many people have worked on this domain adaptation, transfer learning, on the keywords distributional robustness, transfer learning, domain adaptation. Also, there's this thing called transportability, which is more a causal concept. So Cox writes in his comment to Leo Bryman's The Two Cultures paper, which was published in 2001 in Statistical Science, the success of a theory is best judged from its ability to predict in new contexts, in a new hospital. And if you can do that well, people define this to be external validity. If you're able to predict in a new context, you would have high external validity. External validity is different from the classical setting. Classical is you have test data which has the same distribution as the training data. You can use cross-validation to estimate prediction performance. But it's well known since a long time that training data is often not fully representative for new test population. Cross-validation will be biased, it can be very misleading, and for example, Brad Efron has pointed this out in a very beautiful and elegant way in his lecture relating to his International Prize in Statistics Award. So what happens if you just use standard machine learning methods? The point is they're very fragile with respect to external validity. They're very fragile if you try to predict in a new context. So this is an excerpt of the Wild Stanford database and the corresponding paper. So in this table, you see different rows, and each row corresponds to a database, and each database has different sources or different environments. Then you try to do prediction, don't look at the details here, and then you can measure prediction in distribution. This is like cross-validation. You randomly delete some points, you try to predict them, and then you can do prediction out of distribution. How well can you predict a new context? And these are numbers, and when the number is high, it means the prediction is good. If you look at the first problem, in distribution, prediction performance was 47. Out of distribution, it dropped to 31. The second problem, in distribution, 93. Out of distribution, 70, and so on and so forth. So on average, there is a 26% performance reduction if you go from internal cross-validation type performance assessment to external assessment. How well can you predict in a new context? So the question is then, well, how can you improve external validity? And the point is, if you can improve, suppose you can, if you would have high external validity, I come back to Cox, and he would say, well, then it's more successful. Then it will be a more successful algorithm, a more successful theory. It will also be a more causal-oriented interpretation if you read Cox, because a causal system is always valid regardless of the context. And I will provide a bit more details on this view. So the question is, how can we model observed and out of distribution scenarios? How can I model the 200 different hospitals and maybe the new ones which I've never seen in the data? So this is about perturbation models. It's about models, it's not about the truth at the moment, and it will be a bit different from robustness, but there will be a connection which I will make later. Let's assume an oracle world. Let's assume the oracle has a model for the entire system. You have a response variable of interest, y. You have explanatory variables, features, covariates, x. And you have many non-observed hidden variables, which will be definitely in the game in real-world applications. And then you see this influence diagram. Each variable is influenced by another one. So, for example, y is directly influenced by x1, and this hidden confounding variable h1. So suppose the oracle gives you that model. This is only a discrete graph. You can put a quantitative model on the graph, and people typically do this with a structural equation model. This is well known, but I quickly go into that. So you model the different random variables, which are the nodes. Every node is a function of its parental variables, comma, error term. The error term are my epsilon j's. And because I have all the hidden variables in my oracle model, it's very reasonable and plausible to assume the error terms are jointly independent. These are independent stochastic innovations. Now, Judea Pearl calls these structural causal models because he makes a big philosophical step, in my view. He claims this is the true underlying causality mechanism, and hence this is really a causal model. It's a philosophical step to go from this model to claim towards true underlying causality. I'm rather staying away from this, and I prefer the terminology structural equation model. Mathematically, they're exactly the same object. Now, these are nice models. They have good properties. If you ask, okay, the joint distribution in such a model, what kind of properties do they have? Thanks to the joint independence of these error terms, if you have all the hidden variables in the game, the joint distribution satisfies D or A certain Markov property. And if you're interested in the details about these things, this is known since a long time, and it's beautifully explained in Stefan Lauritsen's book on graphical models. So here's an important remark which I want to say. We do not aim to learn the graph from data. That's very ambitious, it's also unrealistic, and it's also mathematically impossible. You can only learn an equivalence class and so on. So in my lecture and also the kind of research we do, we only use these structural equation models to model perturbations. We're not claiming any truish causality. So I want to illustrate what I mean by this. The experts, of course, know this, but I think it's worth going into that. Let me explain to you maybe the simplest perturbation model in these structural equation models, and this is Pearl's do intervention, but it's actually a model. So on the left-hand side, you see a graph, right? It has no hidden variables for simplicity, and then you have structural equations. The last one for y is in red, right? And you can write down these equations according to the graph. Now, we make a perturbation in this system. And one of the perturbation models, according to Pearl, he would write, we manipulate the second variable. And he writes, do x2 equals a value, say little x. Little x can be random or deterministic, that does not matter. So what does this model do now to my problem? First of all, you change the graph. Because you manipulate the second variable, all incoming arrows into the second variable will be deleted. That's a very reasonable assumption in this model. And then this value, little x, you manipulate x2 with little x, it propagates according to the graph structure. You can see this in the equation here. You just set the second equation to this value, little x, and then x1 is influenced by that, and through x1, y is influenced by that, and also it has a direct influence on y in my example. So if you look at this, you realize this is dynamic propagation of an intervention. I manipulate, I intervene at x2, and it dynamically propagates through the system according to the structure of the graph. That's a very good property of this perturbation model in my view. And there's another thing which you may not have realized, but I want to emphasize this. Something happens here, and this is autonomy which we assume. We assume that the structural equations remain the same. That's a huge assumption. In this do intervention model, the intervention value propagates, but the model says the structural equations remain the same. That's a big assumption, but we need to point that out quite clearly. Now, if you go into the literature on perturbation models in these structural equation models, in causality perturbation models, all of them so far, which I know, have this property. It's dynamic propagation of interventions. That's a very good thing. And all of them assume some sort of autonomy. It's the same functions, which may be very unrealistic in practice, but that's what these models are. So let's take a visual break. I learned this from a didactics course. Visual breaks are great things to do. But actually, I prefer snack breaks. It's getting late afternoon. And my snack break is you can discuss a bit this picture, whether if you eat a lot of chocolate, then you may get more successful in your research. And I think you can debate a bit. Well, maybe you're doing a good job in eating a lot of chocolate, and I'm sure you will be great in research and you can pass it on. So you see a perfect correlation here. This is a causal problem, and I'm not too much into causal problems, but maybe it gives you a little break here before I continue. Okay, I hope some of you got the chocolate. I'm sure you will get great research results in the future. So if you have these perturbation models at hand, you can do causal thinking for external generalization. Because these perturbation models give me a quantitative answer to a what if I perturb question. What happens if I perturb? And again, I want to emphasize, I want to answer this question without knowledge or inferring the graph structure in the structural equation model. So now I'm I need the help again, so you have another break. You can you think it's worth shifting it, or okay. Soll ich weitermachen? Soll ich warten schnell? Okay, you have time to eat your chocolate now, so go get it. So
It's just one of these little interruptions that we have here to keep everybody awake. And so now we'll get the talk on my laptop.
okay, es kommt auf beiden. Und wenn der da stuck ist, ist egal. Das ist gut. Okay, good. All right, that was the break, the longer break. So with these perturbation models, we can do now external generalization. Let me try to explain this a bit. Let's consider again this setting. We have multi-source data, like in my intensive care unit prediction problem. I have it from different known observed environments, or experimental conditions, or perturbations, or subpopulations. And they're denoted here in this talk with a little E for an environmental condition, and they're part of a space script E. Script E is the space of observed environments. So my example is my medical ICU data. I have 200 different observed hospitals, centers, or environments, so my script E can be labeled by 1 to up to 200. So what is external validity here? Now we consider many possible but mostly non-observed environments or perturbations from a space script F, which may be much, much larger than script E. Example for such a space script F in my ICU problem, it could be the 200 hospitals, which I have in the large training database, and many, many new ones. And external prediction validity is how well can I predict y given x, as usual, such that the prediction works well or is robust for these new environments, E in script E, which I have never seen in the data. That's somehow the problem. Now, of course, you can mathematize this problem, and for simplicity, I mostly show you concepts for linear models, but then I make remarks about nonlinear machine learning. So for linear models, you could then ask, okay, what is the best regression parameter, beta, which optimizes worst-case L2 risk over all environments, also the future ones, which I've never seen. Nonlinear ML is accordingly. And of course, people would say, well, this is robustness. This is about worst-case risk over a certain class of perturbations. That's true. And it's also about causality because it's about something which you've never seen. It's about a new perturbation which you've never seen, and you can try to predict that perturbation. So here is one of the big theorems, very high level, formulated in a linear model setting. If you look at worst case risk in a linear model over certain class of perturbations, this actually equals what people call the causal parameter. And of course, the question is, what is this class of perturbation? I will show that a bit. But this is an important message because all of a sudden, risk optimization, which is very familiar to many of us, all of a sudden agrees with causality, which is to many of us a bit of a peculiar subject. So what are, again, high level, the assumptions on this perturbation class script f? And this can be best explained in graphs. If you say script f are all perturbations which do not act directly on y, so here's the graph. The perturbations is the E, the environments, they act on X, but they do not act directly on Y. Then this is true. Worst case risk optimization equals the causal parameter. What is the causal parameter? That's the linear regression coefficient in that structural equation where you just have the regression on the parental variables of Y. Now, the experts in the room say, yeah, hey, but this is much more generally true, and that's true, even if you have hidden variables in the game. This is true. If your perturbation class does not act directly on Y and does not act, and here's a huge assumption, does not act on H, on any hidden variable, then worst case risk optimization equals the causal parameter. And on the right-hand side, this is essentially the instrumental variables regression model. So people have, of course, known that. And if you look at this from a bit a different perspective, this is also what people call covariate shift. It's a bit differently formulated. It's formulated here in terms of graphs. This is covariate shift. The perturbations shift X, but they do not shift directly Y or any hidden variable. Of course, it dynamically propagates, but there's no direct shift on Y or H. We will go beyond covariate shift, and I will explain that a bit later. We can do this also for nonlinear models. Let's skip that. So what is the underlying implicit property that this is true, that worst case risk optimization equals the causal parameter? And this actually goes back to Trygve Havelmo. He was a famous person in economics. He later got the Nobel Prize in economics in 1989. Already in 1943, he derived an invariance principle, and he realized in my notation that if you look at the conditional distribution of Y in environment E, and if you condition on the causal variables of Y, the parental variables of Y in environment E, that conditional distribution remains the same over all possible environments if the environments do not act directly on Y and do not act directly on H. So causal, if you would know causal, it implies invariance in this. So this is really different from, okay, let's just look at the conditional distribution on Y given all the X's. If not all the X's are causal, then that conditional distribution will not remain invariant. And from this, it's actually a small step to this optimal risk optimization result. So if we have this, we can go further, and this is what I call causality-inspired invariance regularization, and I can use that in essentially very many or almost any machine learning algorithm. We want to encourage various degree of such kind of invariance from small to large, and one of the main ideas to make it simple is just try to fit your machine learning algorithm such that the residuals become similar or the same, aka invariant, across your different environments you have, across my different 200 hospitals which I have. So why do I call this causality-inspired? Making residuals or conditional distributions invariant has a very clear correspondence with conditioning and causal variables. That was just the slide here before. Okay. So if we try to make conditional distributions invariant, we call this causality-inspired invariance regularization. This recently became a very active area in machine learning. Many people have tried this with more or less success. So how can you do this? It's actually simple, and that's why it can be, it's ready to be used. You just add an invariance regularizer to your empirical risk minimization problem. So what you see here, you optimize over functions. This is for nonlinear machine learning. You look at empirical risk. It looks a bit peculiar, but because I have all my different environments, you just pool the data and look at empirical risk, and you add a complexity penalization with a parameter lambda. As usual, this can be a neural network, could be kernel machines, could be lasso, can be random forest to a certain extent. Now, how do you add inspired causality invariance regularization? The idea is very simple. You add an additional regularizer. You take your empirical risk, maybe complexity penalized, and you add gamma times an invariance penalty. So here's maybe the simplest example of an invariance penalty, which works quite well. So you try to make residuals similar. You just look at residual sum of squares in environment E, and you look at the residual sum of squares in the environment E prime. You look at the difference, and you want to make the difference small across all E and E prime in your observed different environments in the data. So you can do this. This is computationally not so difficult. It's essentially as easy or as difficult as the original empirical risk minimization problem. You can use other invariance penalties. Let's skip that. Okay, so the question is, why should you do this? Well, you can make residuals invariant or conditional distributions. Sounds kind of interesting, but there's actually a much deeper mathematical guarantee in a certain model if you do that. And let me try to explain this a bit. So this causality-inspired invariance regularization can have very rigorous mathematical guarantees if you look in a particular model. And the model we call the anchor regression model. So what is an anchor regression model? So it's just a graph here. I have my y, I have my x's, I have my hidden variables, and I have the E, the environment, they act on the system. And now almost everything is possible. The environments are allowed to act on X to do covariate shift. They're allowed to act on Y directly. They are allowed to act on the hidden variables directly. The only assumption, if you look in this graph, is this E, this perturbation, this environment, is a source node in the graph. Economists would say it's an exogenous force to the system. So it's a perturbation which comes from outside. My different hospitals have a perturbation from outside, and they create something on the system, on your X, Y, and any hidden variable. So this is not just covariate shift. It's much more general, and this is what we call, in a way, everything shift. Everything can shift, but the shift, the perturbation must be exogenous. It must be a source node in the graph. Now you can put a quantitative model on the graph, as before, and then you can ask, what do you get? Well, maybe I should show that slide. You do not get the causal parameter. So people in instrumental variables regression say, hey, this is wrong, this is violation of the instruments, you cannot get the causal parameter. That's true, but you still get out something if you do this. And what you get out is robustness. If you have this kind of perturbation, it's still giving you worst-case risk optimization over a certain class of perturbation models. And I will explain you about this class. You will not get the causal parameter, but you still get worst-case risk optimization. You still get robustness. How well can you predict in the next hospital? So I'm also giving this in a high-level description. So we have a perturbation class, and this consists of a perturbation vector. This is denoted as V, and it has a certain length gamma. This is L2 norm squared, so V gamma is bounded by gamma, or essentially is equal to gamma. So the length of my perturbation vector L2 norm squared is gamma. Now, how does that perturbation act on the system? I take my anchor regression model and just replace my exogenous force, which were my different hospitals. This is now my perturbation vector. It's a source node in the graph. It can be of small size, then it would be a small node. Here I show a large node, which would mean a large perturbation. And then it propagates, as I explained or indicated before, it propagates through the system as before. It influences X, Y, and H directly. So if you look at this perturbation model class, you get out a very beautiful and elegant formulation. Namely, there's a very detailed correspondence between this distributional robustness and this invariant regularization. And the theorem says, for any regression parameter beta and any perturbation vector, which I indicated how it acts on the system, V gamma, it has L2 norm squared bounded by gamma, the worst case risk, if you have that perturbation with this perturbation vector, the worst case risk equals exactly the objective function of your causality-inspired regularization. And the gamma, the size of your perturbation, corresponds exactly to the value how much you regularize. So if you regularize with a large gamma, you protect against strong perturbations and vice versa. So this is very elegant in my view. It's very useful. We also have finite sample results. This equality is true in the population. Okay. So we have extensions of this. You wonder, okay, I claim for better machine learning. We can do this also with nonlinear models, and I'm skipping the technicality differences and details, but you see here a couple of our own work. So it's distributional robustness via invariant gradients. We have nonlinear representation learning. We have also neural adversarial invariance learning. We have also invariant probabilistic prediction, and so on. So in our own work, only the first three allow such a very detailed correspondence between worst case risk, what is it, and the gamma, the regularization gamma. Most results in machine learning is if gamma goes to infinity, I enforce full invariance and then I can prove something. So here we're trying the much harder problem. What can we say for any gamma? If I take a medium range of gamma, what does it correspond for? And we get out similar results as this one here. Okay, so people would say, well, this is kind of interesting, maybe, maybe not, but many people do distributional robustness. And this is indicated here on the left-hand side of the slide. This is well studied in the optimization literature. You try to find the best regression parameter which optimizes worst case risk over all distributions P around a P0, which is row apart according to a certain metric D. So here's the picture. You have a sphere in a postulated metric. The sphere has a radius rho, and you try to solve this problem, and people know how to solve this problem. So this is a good approach. The metric is pre-specified. You take Wasserstein, F divergence, and then you do this. Now, if you look at what we do here with this invariance regularization, it also solves a distributional robustness problem. It also solves worst-case risk optimization. But the metric is learned by the data. The metric is learned by the heterogeneity in the data according to my model in a certain sense. So in my hospital, if, say, blood pressure is very heterogeneous across very many different hospitals, the metric will be stretched out automatically. And if it will be not very heterogeneous with respect to, say, glucose uptake, then it will be very flat in that dimension. And so in higher dimensions, it's quite useful, instead of having the full sphere, we have an ellipsoid metric which stretches out according to what we observe in the heterogeneous data. What if the perturbation model is misspecified? Okay, we have no rigorous answer to this question yet, but I just give you some thoughts, and then I show you how this works. The perturbation model plays no role in the procedure. I can just run this procedure. It gives me something. If I want to have something within the observed environments, I can still enforce conditional invariance of conditional distributions. This is fine. I can check this. I can validate this on my observed environments. If it's about new things which you've never seen, we have no results if the model is wrong. We cannot validate. We simply do extrapolation to the unknown. That's probably intrinsic to the problem. but maybe the model has potential to be useful as an approximation, and I'm sure you all have seen this quote before by George Box. Okay, so how does that work on my ICU prediction problem? This is this domain adaptation which we try to achieve. Can we predict in a new target ICU? How well can we do? And this is just a snapshot. We have many results here, but this is a snapshot. So let's look at the response Y, which is the average heart rate on the third day after ICU entry. We have covariates or features, 4 static ones and about 50 dynamic ones. So you have these time series of blood pressure, glucose uptake, and so on and so forth. The training data is approximately 200,000 samples, approximately 200 different hospitals. And we have this one new target ICU, which is the MIMIC-3 data. It's the hospital in Boston. On the left-hand side, you see the mean squared error. This is the y-axis. On the x-axis, you see the gamma invariance regularization parameter. So this is a bit differently labeled, but gamma equals 1 here means pooling the data. You just take this large database, you pool it, you run your machine learning algorithm, you get a performance on your Boston hospital. Then you increase gamma, you make it more invariant, you improve. And if you make it too large, it will be bad. And that's important to point out. So again, I see many papers which say, well, we do this full invariance, but we couldn't make that work. We can only make it work if gamma is not too large. If gamma becomes large, you protect against very large perturbations, and they simply are not in the data. So the same with 90% quantile squared error. You pool the data, that's on the left, on the x-axis, then you improve. If you make gamma larger, you make more and more invariance. If you make it too large, it will be bad. So adding invariance leads to clear improvements for this particular problem for external validity. Okay, this is not really realistic, of course. You want to have higher accuracy, and you want to see how well would you do if you already have some data, and this is very common also in computer vision. So people have already a few data points on the target domain. So people have already a few data points in my Boston hospital. And the idea here is applied ad hoc. I can just combine this invariance regularization with very classical technique. I can do much better than agnostic prediction if I have a few target data from my Boston hospital. And what I do is I label it as empirical Bayes, or you can also label it as L2 shrinkage. You estimate your best function, f hat, with a certain invariance regularization gamma based on your large database. You have your large database with 200 hospitals. You estimate your best nonlinear prediction function. And then you also estimate the machine learner on the target data. That's the first term on the right-hand side of the argument. But you only have a few target data. You will have a lot of variance. You better shrink it to this F, which you learned from the large database, right? And of course, you can take an empirical Bayes point of view. You can say, okay, my prior is the unknown F. I estimate the prior from the large database, and then I shrink towards the prior. And if it's Gaussian, it looks like this. If I have a few points in a target domain, I can also use cross-validation to choose my parameters. Otherwise, it's difficult. I need to choose a good value for gamma. Otherwise, it won't work. I need to choose a good value for how much invariance regularization do I want to put on the problem. Okay, so here you see 3 examples. The one on the left is the successful, and the 2 others are the not so successful ones. On the left is transfer to the Boston hospital. This is this MIMIC-3 data set, and you see different colors. So the green line is the mean squared error if you just do target data regression with machine learning or linear models as a function of how many target samples you have. If you have more and more target samples, you do better and better by just looking at the Boston hospital. The red one is this empirical Bayes combined thing. I estimate first a good prediction function from my large database, these 200 other hospitals, and then I shrink towards that, and that's the red line. And at the beginning, with very few target points, it does well. And eventually, around 1,000 samples of the target domain in the Boston hospital, they're about the same. The other lines are agnostic. You just use the large database and you try to predict on the Boston hospital. Gray is pooled machine learning. Blue is causality invariance regularized machine learning. So here, trying to transfer to the Boston hospital is successful. At the beginning, if you have only very few data at hand, it works substantially better than just target data regression, and actually also than many other techniques. Then you can try to transfer to other medical domains. This is the MIMIC4, then this is the HIREAD in Switzerland. How well can you learn the prediction accuracy or the prediction model if you train on US database and try to run it in Switzerland? That's on the right-hand side. So the green one is target data regression, and all others have about the same performance. So if you use the large database, it's good. If you have very few data in Switzerland, around 1,000, there is not additional gain. So for this particular problem, and it depends on the problem, if you have less than 1,000, it's worthwhile to go to the large database, try to extract the information. If you have 1,000 or more data points, you cannot see much gain here. This is what's written here. The information worth in this particular problem, in others it looks different, but in this particular one is the information worth of this large external database is about 1,000 samples from the target domain. That's my currency. I get 1,000 samples from the target domain if I go to external large databases. This proposed empirical Bayes approach was almost always among the best. In one case, we could see successful domain adaptation. In the others, we could see a bit less good domain adaptation. This remains to be a very hard problem in practice. So finally, just quickly, I want to switch gears. I talked a bit about machine learning. I want to switch gears from machine learning to building machines. So recently, I became an experimentalist. So together with a PhD student of mine, Juan Gamela, we actually build machines, real machines, or we build physical systems. We call them the causal chambers. On the left-hand side, you see a wind tunnel. On the right-hand side, you see a light tunnel. These are two real physical systems. They're fairly closed physical systems, of course not perfectly, and they're manipulable. So I can do interventions, I can do perturbations, and I can just look what happens in these systems. And in my view, this is one of the things which is very useful, that we get to know how well can we do external generalization, how well can we do causality if we actually can run it on a real physical system. In this real physical system, we have the ground truth in very good approximation, and with these machines, you have an instrument to get to know a bit more about true validation on true systems. Arguably, these systems are simple. They contain only about 20 variables. This is not genomics, this is not genetics, but at least it's not just simulated data, or it's not just AI-generated data. This is real data from physical systems. For you, if you're interested in that, in the near future, there will be public access to these machines, remote access. You can open your laptop, you can access the machines, you can run an experiment, you can do perturbations on these machines, and you get the data, as many as you want. Conclusions. While inferring causality from non-randomized experimental or interventional data is, in my view, often wishful thinking, adding this causality-inspired invariance for statistical methods, estimators, algorithms can be very worthwhile for improved distributional robustness, more reliability, and better external generalizability. Thank you very much.
Thank you very much, Peter, for a very inspiring talk. Questions?
Columbia University. I wanted to ask you, you spoke about world. There's a picture that you showed, the first picture on the slide. It has a badge. Can you tell us about the badge? Because
Do you understand him?
No, you cannot hear me? There is a badge.
Repeat the question again, please.
Oh, yes. So the picture of Abraham Wald, can you put it on the screen? Because you see, I work at Columbia University, and I have seen that picture before. And there's a story behind that picture. So the picture is, he has a badge, like a little card on his jacket. And the reason why he has that was because he was giving a talk at the Army or Air Force, and that was classified information. Now, so that's what you were talking about, was classified information. And anyways, that was all.
Sorry, no. I didn't understand it, and she neither. Okay, it's a comment or, okay, good. Good, so I think we can close it. It's fine.
Sorry, there are some acoustic problems.
It's fine.
So we can try again?
It's fine. I think it's a comment, right? Or, I'm not sure.
Yes, I'm sorry. It was not a question, it was more like a remark. On the picture that you showed, in the jacket of Abraham Wald, there was a badge. There was a little sticker in his jacket.
Can you say again, sorry?
And that sticker was because he was giving a talk about classified information. So, sequential analysis was classified. I'm just making this remark. It was quite important and classified. As you mentioned, it saved a lot of lives.
Good. I see. So, thank you. That's, that was about, that's about Wald, right? Yeah, so it's fine. I think you can have it. There is one there.
Thank you, and I hope there will be others. Based that I am engaged a lot in causality, the question relates how much does this improvement that you have shown depend on the graph, the causal graph, and could it be extended also, that causality is a contested concept, to potential outcomes or to combination with the graphs, which is by Richardson Robbins, right, the Swigs. So can it be extended outside of the DAG context, the modeling?
So you're asking whether one can do the causality and the potential outcome. So that's, I think, a good question. But of course, you can make mathematical assumptions, then run it on the data, and then you can claim, well, this is now my causal effect. If you do this in real applied problems, I'm not so sure whether people actually will really believe it. It may be very useful as a prioritization for experiments. So if you would have access to an experimental lab, it can be very useful. Otherwise, I'm a bit careful in making causal statements, but what I do think is possible is to make it more robust. And robustness is just much less ambitious than saying it's causal. So.
Hi, can you hear me?
Yeah, go ahead.
And it's audible down there. Great. So I was wondering about the last thing you mentioned about the causal chamber, because at least intuitively speaking, when one has a physical model or a model, let's say some computational model for the data generating process, that seems a bit closer to a causal model because one has some more insight about the mechanisms, right? And in scientific machine learning, people are putting efforts to, let's say, infer physical laws from data that were maybe before postulated by some very informed expert. Can you explain whether is there some connection at a high level to what you're thinking about there?
Well, I'm not sure, but I can maybe just try to say again a bit, why did we do this? So first of all, I think it's useful to make this bridge from models, assumptions, simulations, where you can verify whether your assumptions hold, to something where you don't know, right? And or you don't know a priori in your algorithms whether assumptions hold or not. Now these physical systems, they are to a certain extent models, because the light tunnel actually has some sort of physics, so we can look at this established physics model, which is probably true. But even if we don't know, we can run with this machine a perturbation and just measure what this perturbation made. So that's very solid, right? And just your question, what we realized, and we started to do this a bit, okay, you can look at algorithms, you can look how well they do in simulations, and then you can look how well do they do in such chambers, in such physical machines. And maybe not that surprisingly, the results are sometimes very different. And we don't quite know what it is, but apparently the true reality is different than the models. And of course, the question is, how big is the difference? And in our preliminary experience, sometimes the difference is not that large. When we have algorithms, we know, okay, they're good in these kind of models and settings. Maybe this works in the physical system. But for others, we just observe it just don't work. And that's kind of interesting. And of course, it doesn't give an answer at all like what Xi Hong has been talking in the morning. How can we make genomics and genetics better? But it's really in between. It's between simulations and complex reality. We cannot build, or I cannot build model of complex, I cannot build machine of complex reality. I simply cannot do it, but I can build a machine of small, low complexity reality.
So maybe I can ask a
maybe you can close it.
No, there's someone.
I have a more applied question related to your ICU example, and I wonder, another approach, like let's say you have an infinite, or you want to estimate the or predict something in a new hospital given a set of hospitals you've seen before. A classical approach would probably be to use a hierarchical model or a random effects model, where you try to predict the random effect of a new hospital. Because you've seen many hospitals before, and each of them has, some commonality, and you have some random effects or hierarchical model that treats each hospital individually, but then pools to get the common function. Could you comment on whether that approach would be possible at all in this context, or is it just unfeasible?
Did you hear him or you not? What is he asking? Okay, so maybe we postpone the question, just approach me afterwards. Okay, thank you.
Sorry, the sound is a bit difficult to hear from
It's
here.
kind of a bit, it's always this bouncing, right? I think it's fine, you just close it.
Let's see. If there are no other questions, I will ask just a small question, maybe to you. Where do you see the future next big questions in causality? And you mentioned a little bit robustness, but do you see some other main cornerstones which are open? Or
Yeah, well, that's a long story. So maybe just connected a bit to my physical machines. I think there's a lot of activity. We've heard it also in the first plenary talk on, trying to derive equations from data. I think physics-informed machine learning, more domain-informed machine learning. I think that's something potentially very powerful. This is maybe also not that new. Of course, many people who worked in interdisciplinary applications do this since a long time, but maybe this is revived to a certain extent. And putting it a bit in the context of my talk, we hear a lot of, pre-trained models, right? Can we make use of them in particular applications? And you can look at this thing in some sense, okay, my pre-trained predictor was from these large databases, but it could come from very different sources, like, a pre-trained large language model or neural network. And if that would be combined somehow, which this captures the large volume information to your particular problem, that's something at least to me personally looks interesting, but that's not a claim. What's the future of AI?
So let's thanks a lot, Peter, again for a very, very nice talk.
Thank you.
We very much appreciated that you came to Bochum to deliver your lecture. Knowledge from Ruhr University Bochum.
Danke vielmals.
Thank you very much.